Hello, everyone. Welcome to the RS Specialist Discussion Meeting on the MHD oscillations and waves from the photosphere to the corona, organized by Chris and Mihalis and myself from Queen's University Belfast and Robert from Sheffield, with the help from people of the RS, especially Richard O'Sullivan. We would like to thank every one of you for coming and everyone for accepting our invitation, for contributing to the talks and posters. The full program of today's meeting is available in the link I just sent in the chat box. It's a PDF file, so you download from there. Our meeting will be from 10 o'clock to around 7:30. We also have a poster session during the lunch break between 12:45 and 1:15 in the afternoon. The link to the poster, I will send the link to the poster now. And we use WonderMe for questions and answers Q&As for the poster session. Login information for the poster Q&A session will also be available soon. I will paste the information in the chat box soon. And I will be chairing the morning sessions, and Chris will be chairing the afternoon sessions. We have 25 minutes in total for each invited talk, and 15 minutes in total for each contributed talk. So we will remind you 3 minutes before your time is over. For example, I will close my video when you start your talk, and I will show myself again 3 minutes before your time is over. So you know that it's going to be over soon. And yeah, so without further ado, our first invited speaker will be Krishna from KU Leuven on the nature. His talk will be on the nature and the properties of compressive oscillations in hot corona loops. Krishna, please. I'm going to stop sharing my screen.
Yeah, thanks, Jojo. I just want to confirm that even if you show yourself when I'm presenting, maybe I'll not be able to see you, right?
Okay.
Yeah.
Brilliant.
Yeah.
Okay, I will make a noise.
Okay, yeah. All right. Suppose you can see my screen now.
Yes, yeah.
I'll just move this here. Okay. Can you hear me clearly?
Yes.
Okay. Yeah. Thank you very much, Jaja. So let me begin with thanking the organizers for giving the invitation to present my work at this meeting. So I'm Krishnaprasad. I'm an FW postdoctoral fellow from KU Leuven, Belgium. As my title indicates, I'll be speaking on the compressive oscillations in hot kernel loops. By hot, I mean the with loops with plasma temperatures exceeding 6 million Kelvin, on the order of 10 million Kelvin or so. So most of the results I'll be presenting are available in an article at the link shown here. So if you need more details, you can always go back to that article, refer to the, I would like you to refer to that article to understand more details from this presentation. Yes. Okay. Yes. So the outline of my talk is as below. So I'll briefly introduce you to some of the relevant literature regarding these compressive oscillations, some of the past literature. And then I'll discuss whether or not there are different classes of oscillations as shown by some of the recent results. And then I'll also show you the oscillation properties we have extracted from one of our studies, and the evolution of them, how they vary over time. And I'll also be discussing the possible multi-thermal nature of the loop that is apparent from the observed oscillation properties. However, what is not covered in this talk will be the excitation mechanism of these oscillations and the damping mechanism of these oscillations. So I have shown a number of references here. This is not an exhaustive list, of course, but I just want to mention some of the relevant references here. And then I would also like to tell you that briefly about the excitation mechanism, that we have rough consensus that we see these oscillations are typically triggered by a flare or some reconnection event at the foot point, and then there is also they are also associated with an impulsive flow at the beginning of the oscillation at one or both the foot points. And the damping mechanisms, since the early days, it's been mainly thermal conduction has been considered as one of the important damping mechanisms. But then the recent studies also show that this is not always the case. There have been some examples with only viscosity being the dominant damping mechanism. And then of late, there are references from Kolotkov and co-authors and Abhinav Prasad and co-authors. Recently, they published some articles on the misbalance, thermal misbalance, the possible misbalance in the heating function created by this wave, and which in turn can cause damping of these slow waves. So that as one of the possible damping mechanisms that's been discussed in these articles. So I'm not going to discuss neither of these topics, but mainly focusing on the nature and the properties of these oscillations. So to begin with, the compressive oscillations in hot corner loops were first discovered in the Sumer spectra. As you might see on the right here, that the slit spectra at the loop apex, as shown here, showing these Doppler shift oscillations of red, blue alternative Doppler shift oscillations close to the apex of the loop. At the bottom here, you see a similar example, however, with also with the corresponding intensity oscillations at the bottom shown here. An interesting aspect to note here is that the intensity oscillations are phase shifted by about a quarter period, which is a signature of standing slow waves, standing waves. So these oscillations are visible in very hot spectral lines. Like I said, these loops are typically of 6 million Kelvin to 10 million Kelvin or even more. The oscillation periods are of 7 to 31 minutes in the examples this Wang and co-authors have studied. And the damping time are roughly of the one period, roughly of the same order. They also measured the propagation speeds, which are of few hundred kilometers per second. They're approximately of the same order as the local acoustic speed. So based on these results, they were interpreted mainly as standing slow mode waves. Like I said, these oscillations are also triggered by some small flares or micro flares near one of the foot points, some reconnection events. So as you might see in this figure, there are usually brightenings at one or either of the foot points, one or both of the foot points before these preceding the onset of these oscillations. So recent observations with thanks to the high cadence and high resolution continuous observations from AIA, recent observations show these back and forth motions in the loop, bouncing back and forth motions in the loop, as you might see in the movie animation here on the right. So if you construct a time distance map along the loop, this is how it looks like at the bottom, as shown in the bottom. So you see a typical wedge pattern or a triangular pattern in the time distance map representing the motion of this bright perturbation. And you can take cut across this time distance map, and then you can fit a damping sinusoidal function to extract the oscillation period and damping time. So the oscillation period, damping time are shown here. And you can also measure the propagation speed by approximating the length of this loop, by approximately measuring the length of this loop. And using the oscillation period, you can measure the propagation speed of these oscillations. As you might see, the oscillation period, damping time, and propagation speed, these values are roughly on the same order as that has been shown previously for the standing slow mode waves or the compressive oscillations, so-called Sumer oscillations. So similarly, these oscillations are also triggered by a C-class flare at near one of the foot points of the loop. However, from looking at the time distance maps, one might say that these are not standing waves at all. These are, in fact, interpreted as reflected propagating slow mode waves. Indeed, the simulations, some of the simulations to replicate these bouncing back and forth motions show that these are reflected propagating slow mode waves. So Fang and co-authors here, they used a 2.5D MHD simulation to replicate these bouncing back and forth motions here. As you might see, the time distance map similar to the one observed there. They also studied the phase shifts between intensity and Doppler shift oscillations, corresponding phase shifts in these oscillations, and then they showed that these are propagating waves traveling at the speed of local acoustic speeds. So these are indeed reflected propagating slow mode waves. Later studies refer to them as sloshing oscillations, referring to the bouncing back and forth motions between the two legs of the foot points. There is also a similar example by Wang and co-authors where there has been a flare at one of the foot points, as you might see, and they also studied the oscillation period, damping time, propagation speed, and properties. And you see that the properties are pretty similar to what has been observed in the previous case of Kumar et al. 2013, and also in the Sumer oscillations. However, if you look at the time distance map, the pattern is pretty much vertical. The ridges are pretty much vertical, indicating these are sort of standing waves rather than a propagating waves, reflected propagating waves. You can also see that in the in this movie that you can see at some point the half the loop is bright and half the loop is dark, indicating sort of a standing mode here. There have been many examples later with using SDOAA and also Hinode XRT with largely similar properties. Like you can see the bouncing back and forth motions in these different loops, and also in an off-limb loop here from SDOAA. So they all exhibit largely similar properties, but most of them show sloshing type of motion rather than a standing type of property. So the question is, are sloshing waves a different class of oscillations? Like the standing type of oscillations which we see in the case of Wang and co-authors, perhaps they're related to what has been seen previously in the Sumer oscillations. But how are these sloshing waves related? Because they are not standing waves. So are these a different class of oscillations? Completely a different class of oscillations. To address this question, Wang and co-authors performed a 1D nonlinear MSD simulation. So in this simulation, what they did was they used two different models. In the first model, they used the classic thermal conduction and viscosity damping coefficients, and they launched an impulse at one of the foot points, and they see these bouncing back and forth motions like that is seen in observations. But then at a later point, they see a standing mode being set up. Whereas in the second model, they removed the thermal conduction completely and enhanced the compressive viscosity artificially by about 15 times or so. And then they see that the standing mode being set up immediately after the launch of the perturbation, just as they observed in one of their observations. They found in one of their observations. So they argue that these are one and the same phenomena. It just depends on the different physical conditions within the loop. So depending on the physical conditions, either this perturbation might bounce back and forth and eventually forming a standing wave, or it can immediately set up a standing wave. The problem with this interpretation is that we don't see this transformation in the observations. We see either this standing wave being immediately set up, or we only see the sloshing part of the perturbation. Also, some of the earlier simulations by Fabio Reale did not show this transformation from sloshing to standing in their simulations. Also, Nakarikov and co-authors argued that these are distinct phenomena. They're not the same phenomena. They're not the same phenomena. In their study, they decomposed the spatial harmonics at each temporal position, and they studied the damping of different harmonics. And as you might see here on the plot, in the plot on the right, that the amplitudes of these oscillations as a function of time. The solid lines, by the way, are from these observations on the left, whereas these symbols, these triangle symbols, show the expected damping for different harmonics according to a slow mode thermal conduction damping. So you, according to the observations, in fact, so you can see that the different harmonics, different colors represent different harmonics. So the different harmonics dissipate same way as the fundamental harmonic here, represented by the blue, same way. Whereas the expected damping for a slow wave is that the higher harmonics will dissipate faster. So they argue that there is some competition between these damping of higher harmonics with respect to some nonlinear effects. For example, if the fundamental has higher amplitudes, they can and it is nonlinear, it can cascade the dissipation to higher and higher harmonics. So by dissipating the fundamental harmonic fundamental wave much faster than the higher harmonics, or at least at the similar pace. So they argue that that's perhaps might be happening here, and they are indeed a distinct phenomena. They are not same. So to understand this, what we did was we went back to the sloshing perturbation, or the sloshing observation by Kumar and co-authors, the first observation. So we also constructed a time distance map here from the same loop they studied, and we see this typical wedge pattern what they observed. However, if you see the 94 angstrom channel, a similar wedge pattern is observed. However, but at a later phase of time, you see this vertical ridges resembling a standing wave. So indeed, there is a transformation from this sloshing perturbation to a standing wave. So what we did here is that, I mean, the Kumar and co-authors, they studied the oscillation is up to this particular time, where they perhaps based their observations mainly on the 131 channel, although they studied both the channels. So they perhaps based mainly on the 131 channel. They studied only up to this particular time where the damping, the oscillation is visible in the 131 channel. We extended these observations, and then we did in fact see this transformation. So they are likely one and the same. So since we see these two different phases of oscillation, we thought we will extract the oscillation properties differently. So if we extract the light curve from the standing phase of the oscillation, it looks like a typical sinusoidal damping. And then you can see the oscillation period and damping time. If we do the same during the sloshing part of the perturbation, it's non-sinusoidal. These non-sinusoidal behavior has been observed in almost all observations in the previous case. Like you see, even in the first observations of Kumar and co-authors, you see this flat bottom kind of profile. So this is of course because of the bouncing back and forth motions. It's not a general sinusoidal wave. So to replicate this behavior, we constructed a toy model where we assume the perturbation as a Gaussian, and it bounces back and forth between the two ends of a line segment. As you can see on the top, if we plot a time distance map from this model, it roughly replicates what we see in the observations. So using this model, we fit the oscillations, so we can pretty much replicate this flat bottom kind of profile, and we can fit the observations to measure the oscillation period and damping time. So the top panel shows the results for the 131 channel, and the bottom panel shows the results for the 94 angstrom channel. The damping time in the 94 angstrom channel is almost twice as large, although the oscillation periods are roughly the same in both the channels. So we also measure, we also try to estimate the temperature and density of the emission measure using the differential emission measure analysis of this loop. So we see that by taking a box at the loop apex, we plot the temperature evolution over time here on the right. As you might see, the gray dots, by the way, represent all the values within this box, whereas um, the red diamond symbols show the mean values at each temporal position. As you can see, the temperature at the loop apex drops from about 12 million Kelvin to about 6 million Kelvin during the course of this oscillation. The emission measure or the density also drops over time, but the temperature, more importantly, drops significantly from about 12 million Kelvin to 6 million Kelvin. So if we consider, I mean, because the temperature drops, the propagation speed is expected to drop. And if the propagation speed is speed drops, because the wavelength is constant, the oscillation period is bound to increase. So we did see the oscillation period in the 94 channel from sloshing phase to standing phase increase from about 600 seconds to 790 seconds. So the increase in oscillation period is by a factor of 1.3, whereas the corresponding decrease in the sound speed, if you measure about 1.28 or so, which is in good agreement, I would say. So similarly, we also estimated the damping times from the theory by solving the full dispersion relation at these two different phases, and tried to compare them with the damping times we observe in the we found in the observations. So as you might see, these on the right, this tau prime represents the damping times we estimated uh, from the theory, assuming thermal conduction as the damping mechanism according to these two different temperatures in the two different phases. So we see that these numbers are roughly the same as we find in the observations. So they agree pretty much with the observations. So it looks like thermal conduction is the damping mechanism in this particular scenario. Another interesting aspect is that okay, so there is this oscillation is damping according to thermal conduction, and there is transformation from sloshing to standing perturbation. But why is the difference so drastically different when we look at two different channels? When we, on the left, you see the 131 channel, and on the right, you see the 94 channel. So if we look at only the 131 channel, we might say, oh, it's just a sloshing perturbation. But if we look at the 94 channel, oh, it is indeed a sloshing perturbation transformed into a standing wave. Why is the behavior so drastically different? Of course, as we have seen, the amplitudes are rapidly dropping in the 131 channel as compared to the 94 channel. That is one of the reasons, but not the complete reason. Another reason here is that if I plot the intensities, the average intensities in the same box here for the 131 and 94 channel, you can see the intensities suddenly grow at the flare onset, and from this point, as the oscillation begins, the intensities rapidly drop to the pre-flare levels in the 131 channel by about this time, by when the oscillation disappears. See, in contrast, in the 94 channel, you can see the intensities gradually grow, and then they don't drop as sharply as they drop in the 131 channel. Of course, this is a consequence of the temperature dropping, temperature of the plasma dropping. On the right, you see the corresponding response functions in the 131 and the 94 channel. You can see that the 131 channel is sensitive to the plasma about 10 million Kelvin, whereas the 94 channel is sensitive to the plasma about 6 million Kelvin, sorry. So because of this, the intensities are also maintained at a good level to see the perturbations, later perturbations in the 94 channel, whereas we don't see the same in the 131 channel because the intensities themselves drop to a very low level. This also shows that you have different behavior. These two maps also show that you have different behavior in these two different channels. Of course, the damping times, as you might have seen, also different in these two channels, drastically different. They're like twice as much in the 94 channel. All this indicates that there is multi-thermal behavior in this particular loop. So to summarize, the sloshing oscillations observed earlier by Kumar and co-authors actually transforms later into a standing wave when you observe in the 94 channel. suggesting that sloshing oscillations are not a different class of oscillations. So we also study the damping times and the oscillation period between the two phases, and they're longer. The oscillation periods are longer, and the damping times are larger in the later phase, which is the standing phase. And we have shown that these are compatible with the damping of slow waves via thermal conduction in a cooling plasma. We also see the differential behavior present indicates the multi-thermal nature of the loop. The standing phase of the oscillation is not detectable in the channel due to temperature sensitivity of the cooling plasma, besides the rapid decay of the oscillation observed. So thank you very much for your attention. That's all I have to say.
Thank you, Krishna. We have a question in the Q&A from Inigo. He asked, could the transition between the sloshing and the standing regimes be used to diagnose thermal conduction and or viscosity parameters?
Yes. So if we, I'll just repeat the question. So whether the transition can be used to measure the thermal conduction or the viscosity or transport coefficients. In principle, yes. So it has been done by Wang and co-authors in their particular case to measure the viscosity or to give an estimation on the viscosity coefficient. So if we understand these damping mechanisms clearly, then we can measure. That's the main, that's one of the goals of this analysis. Yes.
Yeah, okay, thank you. We have a little bit time for more questions. Okay, may I ask one question? So could the parameters of the oscillation, including the period and damping and temperature and density, be used to measure the magnetic field strength? Would that be possible?
Yes, for a standing wave, it has been shown that assuming that because in these hot loops, the plasma beta is not very low. So you can assume that they propagate not just at sound speed, but at tube speed. So by measuring the density and other parameters, you can estimate magnetic field, yes.
Okay, thank you. And we have another question from Paul. Is there any indication of cross-field mechanisms?
Sorry, cross-field?
Cross-field mechanisms.
I do not understand what cross-field mechanism is. There is an indication of differential properties across the field for sure, but I do not understand what a cross-field mechanism is. I'm sorry. Maybe the person can.
Yeah, I guess you may continue to discuss in the chat box after your talk. And yeah, Krishna, thank you very much.
Thank you.
Yeah, and our next speaker will be Ashonia, and the talk will be on MHD wave amplitude modulation in fan loops as observed by SDOAI. Yeah, Ashonia, please.
Yes, can you see my screen?
Yeah, yes.
Hello, yeah. Okay, so good morning, everyone. First of all, I thank the organizers for providing me with the opportunity to present my talk at the prestigious RAS Society Specialized Discussion Meeting. So myself, Ashwanya Sharma, I have recently, last year, I have completed my PhD and joined a college, Bahana College in Assam, in my home state, as an assistant professor. So today I am going to present our work on MHD wave amplitude modulation in fan loops. Just if you don't mind, can I switch off my video? I'll switch it. I will switch it on again.
Yeah.
Yes. Yeah. I think I cannot switch it off. Okay. Anyway, so before going into the details of my talk, here is a brief introduction on fan loops and propagating waves observed along fan loops. So fan loops are coronal magnetic structures observed at the edge of active regions. They are mostly rooted in the umbra and umbra-penumbra boundary of sunspot. So one of the wave modes observed along these fan loops are slow magnetoacoustics waves. These slow magnetoacoustics waves, they are compressional waves, and they appear in the form of intensity oscillations. They propagate along those field lines and with subsonic speed. Now this slow magnetoacoustics waves in the form of intensity oscillations along fan loops were observed first by Bergsman and Clegg using the EIT SOHO in 195 angstrom. These intensity oscillations or these slow mode magnetoacoustics waves, they are mostly dominant around 3 minutes, whereas however, few studies have reported longer period oscillations also along them. Okay, so in this study, as I have said earlier, we have done a detailed study to understand the spatiotemporal evolution of propagating intensity waves, which propagate along those field lines. The study has been carried out by Atmospheric Imaging Assembly on board Solar Dynamic Observatory, and this is our analyzed active region, which consists of a positive polarity sunspot. And this is the whole analyzed active region is shown in different AIA channels. We can see fan loops emanating from the sunspot umbra as well as umbra-penumbra boundary also. So to study the propagating intensity waves which propagate along these fan loops, we employ time distance analysis technique. So in this technique, we draw artificial slits along along the coronal structures, and to detect those fan loops, we use AIA 171 angstrom, as the fan loops are best seen in AIA 171 angstrom, and we have drawn 3 artificial slits. This whole study has been done in all the AIA channels for all those artificial slits, while in these presentations we are showing our results only for slit 1 and in AIA 171 angstrom for gravity. Okay, so this is the resulting time distance image that we got against slit 1. So first of all, we can see clear propagation of intensity oscillations in the form of bright and dark ridges along this slit. We have measured the propagation speed of this intensity oscillation, and we got it around 50 km per second. We have measured the phase speed by 2 methods, one by drawing slopes along these ridges, as well as by cross correlation analysis, and we found that both the methods give similar results. And second thing is, as we find that this intensity oscillations are propagating along those field lines, they are propagating along these fan loops, they are compressional in nature, and they are showing subsonic phase speeds. So from this, we can claim that this intensity oscillations are slow mode magnetoacoustic waves in nature. Now, apart from the usual propagation of this intensity oscillation, if we see it, if we notice it, we find that there is an overall increase and decrease in intensity of this intensity oscillations over time. It becomes more clear in the light curves. If we extract light curves from this time distance map, say from these locations L1, L2, L3, and L4, this is what we see. So this left columns, they show the original light curves, and once we subtract these backgrounds, we get this deep-rendered light curves in the right columns. So here we can see that there are very clear propagations of 3-minute oscillations for all those locations. Along with that, there is an overall increase and decrease of this wave pattern over time. Means there is a very clear, distinct modulation. Now, to understand the origin of this modulation in detail, first we employ Fourier analysis. This is the Fourier power spectrum obtained from the original light curve. We are showing the plot only for one light curve from one location. So what we see, the Fourier power spectrum shows multiple nearby frequency peaks within 5 to 6 millihertz, say F2, F3, F4, along with many nearby frequency peaks within 5 to 8 millihertz, means 2 to 4 minutes. So now the question comes, the findings of many nearby frequency components lead us to postulate that the phenomenon of beat may be a reason behind such amplitude modulations. Beat is a phenomenon which happen when two nearby frequencies, say f dash and f double dash, they interfere, giving rise to a bit frequency fb is equal to say f dash minus f double dash. Now, if we consider that the phenomenon of bit is contributing here, and we consider the combination of these different frequency components, say we are considering these three dominant frequency components, f2, f3, and f4. So the bit frequencies that we get is around that we get, they are like 29 minutes, 55 minutes, 62 minutes. Now, this 29 minute is something which, if we look at the light curves of this modulated light curves, and if we look at this period, this is something which is nearby this 29 minute. However, we are finding along with this 29 minutes, we are finding some longer periods like 55 minutes, 62 minutes also. So again, I would like to say that the solar atmosphere is very complex and very dynamic. So it is again difficult to say that only one bit frequency is contributing to the overall bit phenomenon. But again, along with this, if we consider the combination of this, one of the say major frequency peaks with this nearby frequency peaks, we find bit frequencies around like 0.55 millihertz, which is around 13 minutes, then this 13 minutes and 8 minutes. Now, regarding this 8 minutes or 13 minutes, I would like to say that Stenberg et al. 2010, they have reported like 8-minute oscillations along loop-like structures, and they've said that like it may be the bit phenomenon which is happening between the chromospheric 3 minutes and the photospheric 5-minute periods, which are leaking into the corona. However, regarding the origin of this 13 minutes and longer period waves, they didn't mention anything. So observations of these many nearby frequencies and getting bit frequencies around 29 minutes, like 13 minutes, this minute, say that bit may be a phenomenon, bit may be a reason behind such observed amplitude modulation. Then we perform wavelet analysis also. Wavelet analysis gives temporal variation of intensity. Here the top panel, this is the detrended light curves, and this bottom left panel is a wavelet spectrum panel, which gives variation of period with time. And this is the global wavelet panel, which is the wavelet power average over the whole period, whole time duration. So what we see in the wavelet power spectrum, we see that most of the powers, wavelet powers, lie within 2 to 4 minutes, and and they were dominant and they were dominant in mostly in 3 minutes. And along with this 3 minutes oscillation, there were an increase and decrease in the wavelet power also, which was simultaneous to the observed amplitude modulation. Now, to quantify this modulating period, we employ particular approach. We, in the Fourier power spectrum, we have seen that most of the period lies within 2 to 4 minutes, and the wavelet and this wavelet spectrum also shows that this is the 3-minute period which is oscillating. So therefore we have taken the wavelet power averaged over 2 to 4 minutes. Now we believe that the wavelet power, which was averaged within 2 to 4 minutes, that will essentially mimic an amplitude variation caused by all the waves between 2 to 4 minutes. Then we perform wavelet analysis on this resulting amplitude wavelet power, and we found that yes, there were oscillation this time also, and this time we got the period around 22.24 minutes, and which was also above 99% confidence level. So from this, and this is how we have quantified the modulation period, and we have found that for other AIA channels also, and for all the artificial slit, and for the different locations also, the modulation period was lying in between 20 to 30 minutes. Now, along with this modulation, in this study, we have spotted some high frequency components also around 11 millihertz, means 1.5 minutes. These were the high frequency oscillations. Now, this 11 millihertz is something which is double of the fundamental dominant frequencies, around 5.56 millihertz. So it indicates, it says that it poses a question that whether they are the second harmonics, as we are finding it as this higher frequency components are double of the fundamental frequency. But again, then question comes, Krishna was mentioning, we are not finding the bouncing back of the waves in the time distance plot first of all, and standing waves to have high to become second harmonics, they need to be standing waves, and and these were like fan loops, though they were somewhere at faraway distance they are connected. And so far standing waves are more so far most of the standing waves have been reported with coronal closed loops only. So we need some further investigation to claim that they are second harmonics. So to summarize, in this study, we have seen clear propagation of intensity waves in different AIA channels, and we have measured their phase speeds and found that they are slow magnetoacoustics in nature. Along with the usual propagation of intensity waves, we found distinct amplitude modulation. We performed Fourier power analysis and found that many frequency components around 5.5 millihertz, which supports that the possibility, which supports that bit may be a reason behind such observed amplitude modulations. Then we have performed wavelet analysis also, which also shows an increase and decrease of the wavelet power around 3 minutes simultaneous to the observed amplitude modulation. The modulation period that we have found was in between 20 to 30 minutes. Along with this, modulation, we have found some high frequency components also in this study around 11 millihertz. And to our knowledge, although earlier studies have reported such amplitude modulations in Fourier filtered light curves and performed further studies, but in this study, these modulations were clear enough to detect them in their original light curves, although the whole study we have done on the deep trended light curves. So that is all. Thank you.
Okay, thank you. Perfect timing. Yeah. Questions or comments? I think Krishna has a question.
Yes. Hi, Aishwarya. Thanks for
Hi.
the talk. So I have two questions. One is on the origin of this high frequency component. You
Yes.
rightly said that these are not standing waves, so you don't expect higher harmonics. But then the driver itself could be a standing part. Like for example, the P modes are the standing modes. So if the P modes are the drivers, they themselves have higher harmonics or multiple high frequency components in the photosphere, and these are what I suspect these are the frequencies that are propagating to the higher atmosphere. So it need not be the locally standing wave, but they are from the P modes. And I have my second question is regarding, you mentioned the longer period oscillations, 13-minute and then 30-minute or other oscillations.
Yes.
Did you say that these are the amplitude modulation as the driver of these oscillations?
Sorry, these amplitude modulations?
You said longer period oscillations like 13-minute or 8-minute observed by someone else. So did you
Yes,
say that?
yes.
Did you say that these longer periods are driven by amplitude modulation, or?
Uh, no, not amplitude modulation, but like for this 8 minutes, like people like 3 minutes, 5 minutes, we can explain the origin of all those oscillations. But when it came to 8 minutes or something, so earlier studies had said that maybe bit may be a reason behind such observed oscillation in the Fourier filtered light curves. That this bit may be a reason, or this amplitude modulation may be a reason behind such observed 8-minute oscillations. But they didn't mention about like 13 minutes, 24 minutes, and all those. But in our study, as we are finding many nearby frequency peaks, and we can see that from the combinations that these 30 minutes, even those 13 minutes, 8 minutes, and even some 16 minutes also, those things at least can be explained from the bit phenomenon. So we suspect that bit may be a reason, yes. Although we need some further statistical study also to
No,
claim
I
this.
don't. Sorry, I don't think the amplitude modulation can be reason for longer period oscillations. If you have an oscillation period and amplitude modulation, they both are different things. Like you can take a sine curve and modulate it with a different period, and if you take a Fourier transform, all you will be seeing is the oscillation period itself, but not the amplitude modulation. Similarly, if you take a amplitude modulation period of 30-minute or whatever, if you take the light curve itself, the oscillation period is different, but the amplitude modulation is completely different. We can discuss this
Yeah.
later if you want.
Yes, yes, true. Yes, yes, yeah.
Okay.
Yeah. Yeah. Okay. And we have a question from Tim. Thank you for your talk. Could you talk a little more about the detraining, please? Could this trend be caused by a very long period beating? I am also concerned about the wavelet 2 to 4 minute filter on the detrained data. Does the 1.5 minute component still appear if you apply the 2 to 4 minute filter on the raw light curves?
Sorry, can you repeat the questions?
Yeah, the question is, could this trend, so the detrending, yeah, could this trend be caused by a very long period beating?
Could it?
The last question, sorry, the last question is, does the 1.5 minute component still appear if you apply the 2 to 4 minute filter on the raw light curve?
Yeah, so regarding the this you're asking, right, 1.5 frequency oscillations. So if we apply, what was the question?
Does the 1.5 minute component still appear if you apply the 2 to 4 minute filter on the raw light curves?
If I apply 2.4 minutes filter on the raw light curves.
Yeah. Does the 1.5 minute component still appear?
I don't know. I have to check. So here we are using 30 minutes. So this was the original light curves. And if I use 2.5 minutes filter, I don't know. I have to check.
Okay. Okay. Sorry. We don't have more time for questions. So yeah, you may discuss in the chat box. And
Sure,
thank you. Yeah. Thank you for the talk. Our next speaker will be Inigo on Bayesian evidence for the nonlinear damping of coronal loop oscillations. Inigo, please.
Okay, good morning.
Are you sharing your screen?
Yes. Can you see my screen?
Yeah, great. Yeah, yes, thank you.
Okay, so good morning, everyone, and thanks to the organizers for the opportunity to present my work. The title of my presentation is Bayesian evidence for the nonlinear damping of coronal loop oscillations. So recent observational and theoretical studies have shown that the damping of transverse coronal loop oscillations depends on the oscillation amplitude. In the last years, the increase in the number and quality of observations have enabled to construct catalogs with a large number of loop oscillation events. What we see when we plot, for example, the damping time over the period as a function of the amplitude for these events is that the data are scattered, forming a cloud with a triangular shape, and in general, larger amplitudes correspond to smaller damping ratios and vice versa. Also, in theory and in numerical studies, it has been seen that the damping of transverse coronal loop oscillations depends on the oscillation amplitude. So for example, in the numerical simulations by Norbert Magyar et al., we can clearly see that for small amplitudes, linear resonant damping gives a good approximation to the damping properties, while for larger amplitudes, the nonlinear evolution leads to a significantly faster damping than that predicted by linear theory. In a recent analytical study by Van Dorselaar et al. In 2021 now, just a few months ago, they have shown that the nonlinear damping of kink oscillations, of standing kink oscillations in coronal loops is inversely proportional to the oscillation amplitude. And the discussions about how good the models are in reproducing the observations are mostly based on the best fit of this upper boundary that's for simulated loop damping and in comparison to the observed data. So in this study, what we did is just to consider two damping models, two simple damping models. On the one hand, we have linear resonant absorption in the framework defined by Ruderman and Roberts and Gossens et al., and based on the thin tube and thin boundary approximations. And on the other hand, we have the recently developed formulae by Van Dorselaar et al. For nonlinear damping in a framework that uses the Elsasser variables. So both models provide us with analytical expressions for the damping time over the period as a function of equilibrium parameters such as the density contrast, the transverse inhomogeneity length scale, the radius of the loop, and the amplitude of the oscillation. So what we do in this study is to confront the theoretical predictions with observed loop oscillation properties in the plane of observables defined by the damping ratio and the oscillation amplitude. And the aim is to quantify the evidence for nonlinear damping relative to resonant damping. Our judgment on the evidence in favor of any of the two models in explaining the data relative to the other is based on the use of Bayesian reasoning. So given a model M proposed to, with parameter set theta, proposed to explain a given observed data D, the marginal likelihood is a measure of relational evidence. And it is computed by just taking the integral of the joint distribution for parameters and data and integrating over the full parameter space. I say that this is a measure of evidence that is relational because what we do is to examine a relationship between the predictions of the model and the data that were observed. So we will calculate this quantity for the two models under consideration, the nonlinear damping and the resonant absorption. The most general model comparison problem, however, is performed when we measure the relative evidence of alternative models in explaining the same data. And if we consider that the two models under consideration are in principle equally probable a priori, then this is achieved by the computation of the so-called Bayes factor, which is nothing more than the ratio of the marginal likelihoods. Here a logarithmic scale is used usually, and then once this number is computed, one can translate the Bayes factors into levels of evidence using an empirical table such as the one by Cass and Raftery. So in our analysis, there are two parts. In the first part, we calculate the marginal likelihood for each model and the Bayes factor, the ratio of these marginal likelihoods, over a two-dimensional synthetic data space in the plane of observables of damping ratio and oscillation amplitude. And this provides a bird's eye view first of the evidence distribution, how evidence is distributed in this plane. In the second part of the analysis, we compute the Bayes factor for the 101 loop oscillation events in the catalog by Nishaeva et al. That have information on both the oscillation amplitude and the damping ratio. To do the calculations, we first need to prescribe our prior information about the parameters and the data generating model. So for the likelihood function, we consider an exponential function for the damping, for the generation of damping ratio values as a function of equilibrium parameters for both models, the resonant damping and nonlinear damping. And concerning the priors in the unknown parameters, we will consider uniform priors in implausible ranges for the radius, the density contrast, and the transverse inhomogeneity length scale. Moving to the results, these two figures show the distribution of marginal likelihood for nonlinear damping and linear resonant damping over the synthetic data space of damping ratio and oscillation amplitude. The magnitude of each of these surfaces at a given point is a measure of how well each mechanism is good, how well each mechanism predicts a particular combination of damping ratio and oscillation amplitude. So we can clearly see that nonlinear damping is good at predicting data in this area here, the contour plot, that contains combinations of, for example, small amplitudes with large damping ratios, but also small damping ratios and a broad range of oscillation amplitudes. Concerning linear resonant damping, the mechanism is good at predicting damping ratios that are small, and then the predictive capability of the mechanism decreases. And the marginal likelihood is, of course, independent of the oscillation amplitude, because the model we are using is independent of the oscillation amplitude. So if we now compare the regions of highest marginal likelihood for the nonlinear damping with the location with the broad location of the data in the Nishaeva et al. Catalog, what we find is overall good agreement between the location of both quantities. If we take the ratio of marginal likelihoods, what we get is a distribution of evidence given by the Bayes factor. Each of these surfaces gives the position in data space where the evidence supports one mechanism or the other. So it is apparent that these regions are clearly separated, they are clearly disconnected, so that an evidence assessment can be performed. For nonlinear damping, evidence is in favor of nonlinear damping is supported in this region here, again with a somehow triangular shape. And the evidence supports linear resonant damping in two regions. One is this small region here that contains combinations of very small amplitude oscillations and strong damping. And the other one is all this region that is the complementary one to this, that goes to the right and top from this boundary here. So here the evidence supports nonlinear damping, and in the rest of the domain, evidence supports resonant absorption. You might be surprised by the large values for the Bayes factor in this region, but this is not much a merit of resonant absorption in this region, but a demerit of nonlinear damping in this region. If we go back to the distribution of marginal likelihoods, it is not that resonant absorption is good or particularly, especially good at predicting observations in these regions, but that nonlinear damping is especially bad at predicting observables in this region. And that's why the Bayes factor in this region is high, at about 50. Again, we can compare the distribution of the data in the Nishaeva et al. Catalog with the region where the Bayes factor for nonlinear damping is high, and we see that there is overall a good agreement. So this was the first part of the analysis in which we considered synthetic data. Now we go to the application to real data. As I said, in the catalog of Nishaeva et al., there are more than 200 loop oscillation events, but for only 101 of them, we have information on both the damping and the oscillation amplitude. A partial listing is shown in this table. So we have information on the period, damping time, damping ratio, oscillation amplitude. And following the same method as with the synthetic data, we can now compute the Bayes factor for nonlinear damping relative to resonant absorption. And these are these numbers here in this column. A positive number here means evidence in favor of nonlinear damping. A negative number means evidence in favor of resonant damping. And again, we can use the table by Cass and Raftery to translate the numbers into levels of evidence. These two figures here show the cases from the catalog by Nishaeva et al. In which conclusive evidence is obtained. By conclusive, I mean that the Bayes factor is larger than 2. So we have positive, strong, or very strong evidence. These cases here are the 49 cases for which there is positive evidence for nonlinear damping, and you see that they are distributed in the region where the synthetic data analysis showed evidence in favor of nonlinear damping. These 6 cases here are the ones for which strong or very strong evidence is obtained for linear resonant damping. And again, you see that they are located in the region where it is not the merit of resonant absorption, but the demerit of nonlinear damping that makes these Bayes factors high here.
Sorry, 3 minutes.
Yeah, thank you. So finally, this is the a plot showing the results for all 101 oscillating loops. Here, the red colors in the plane of observables. Here, the red color means evidence in favor of nonlinear damping, and the blue color means evidence in favor of resonant absorption. The full circles means that the Bayes factor is larger than 2, and then this evidence is conclusive. And the edge-colored circles means that the Bayes factor is less than 2, and then the evidence, even if the marginal likelihood for that particular model is higher, the evidence is inconclusive. What we can see is that first, in the majority of cases, the marginal likelihood for nonlinear damping is larger. These are 87 cases. And second, that the cases with conclusive evidence for nonlinear damping, which are 49, outnumber by a factor of 8 those cases with conclusive evidence for resonant damping. So in conclusion, this is a summary. The structure of the Bayesian evidence in the plane of observables for damping ratio and oscillation amplitude displays a clear separation between the regions where one model is more plausible relative to the other. In our synthetic data analysis, we have seen that there is a qualitative agreement between the regions of both highest marginal likelihood and Bayes factor for the nonlinear damping model and the location of observed data. In the quantitative application to real observed data with 101 events, we see that the marginal likelihood for nonlinear damping is larger in the majority of cases, in 87 out of 101. And the events with conclusive evidence for nonlinear damping outnumber considerably those in favor of linear resonant absorption. So I would conclude that nonlinear damping is a plausible explanation for the observed properties of damped transverse loop oscillation. Thank you very much for your attention.
Thank you. We have a question from Richard.
There you go. Nice work. I guess I didn't understand your results. So if you go back a slide. So you find the strongest evidence for resonant absorption where you have the largest amplitudes and the strongest damping. To me, that would suggest nonlinear, because you have the largest amplitudes, which obviously leads to nonlinear effects, and you also have the strongest damping in that case. And then for the lower amplitude waves, you see sort of more strong evidence for nonlinear damping. It seems opposite to me.
Yeah, but I think that that's it might be that the reason why the interpretation is not clear in following your argumentation is like you are making an argument thinking about the direct problem. So if I have large amplitudes, nonlinear damping should be important. So then I don't understand why I get this strong evidence for resonant absorption. But of course, when solving the problem, model comparison problem using these Bayesian statistics, we are not making arguments in terms of physical feeling or physical arguments. I mean, what we are just doing is just comparing the capability of a model to reproduce some observation. So how far or close the predictions from the model are in comparison to the observation. And then this in absolute terms, and then comparing to another mechanism. This is done with the Bayes factor. So of course, the models we are using are imperfect. For example, a resonant absorption model does not consider a modulation of the prediction in terms of amplitude. So one could say that from a modeler's point of view, we are doing wrong in modeling this data with linear resonant absorption. What I mean, I don't know if I am explaining well, but what I mean is that the interpretation of these results should be done in terms of marginal likelihood of Bayes factors. So statistically speaking, in a Bayesian sense, what these results are telling me. They are just telling me that if my data set is inside this region, then one model is better in predicting observations that were observed in absolute terms, and also it is better in relative terms in comparison to the other. And here, that's what I said. I'm not saying that resonant absorption is good in this, in explaining this data. As we are taking the ratio of two marginal likelihoods, it is not a merit of this mechanism, but probably a demerit of the formula, of the formula, of the analytical formula we have used for nonlinear damping, that is not as good as predicting this region. I don't know if I explained, if I answered your question.
Well, you answered it. I'm not sure I 100% agree,
Okay.
but yeah.
Okay, thank you. Yeah, there are questions from Tom and Andrew and Robert, but sorry, we don't have time for that. But Inigo, you may answer directly in the Q&A. So
Okay.
type in your answer. Yeah, thank you.
Yeah,
thank you for your talk. Yeah, and our next speaker will be Alex on the topic of kink oscillations of coronal loops. Alex, please. You're muted, I think.
Can you hear me? Can you hear me?
Yeah, no, yes.
Oh, fantastic. So,
yeah. Okay.
So today we'll talk about kink oscillation of coronal loops, and in some case the effects of cooling, why it's important and to be considered in studying kink oscillation of coronal loops. So, introduction. So, since 1999, like there were observed kink oscillation of coronal loops, and they were heavily damped. And the proposed mechanism is resonant absorption. It was proposed well before first observations were happened in 1988, and it shows that coronal loops can be damped, and quite heavily with various profiles like exponential and Gaussian. And the more recent theory, for example, Ruderman in 2011 showed that cooling can slightly amplify the damping profile, but of cooling loop oscillation. However, it was even later by Shkhobotsky and et al. It was shown that the combination of cooling and coronal loop expansion could lead to further amplification and deviation from the Gaussian exponential and combination of Gaussian and exponential damping profiles. So later, this theory was studied on one case of cooling coronal loops by Nelson et al. So this is the event. So across spectrum, we can see that the intensity is fading in all the spectrum presented here, and we use a slit technique to analyze the damping to see what is the damping profile. And we want to see if the cooling effect is important to be able to reproduce the amplitude variation through time of the kink oscillation of this loop, of transverse oscillation of this loop. So that was done in 2019. So we pick up the slit, we analyzed it with the Canny edge detection method. We plotted the points. We took the average between the edges of the coronal loop as a tracking point for oscillation. We detrended it using spline technique, and we plot displacement to profile to see how loop is displaced through the oscillation. And although it's quite marginally tiny, we can see that in some cases there is even amplification on the oscillation profile. So and then we compared it with theory proposed by Shkhobotsky et al. In 2011 to see if there is a difference, big difference between the observed profile and theoretical profile, and we concluded that there is no much difference, and one of the important parameters which shows that the deviation from standard profile is the density ratio between the internal plasma and external plasma and the loop fault point. So that was modeled by theoretical model. So what kind of theoretical model was used there is a simple standing wave models. It's a linear model. The magnetic flux tube was considered with internal region, external region, and transitional region where resonant absorption happens. It has density stratification. This is variable cross-section. The magnetic field depends on the radius and the Z component, as well as other parameters. There is background flow, and we use thin tube approximation. So even such a simple theoretical model can provide a reliable result and be comparable with observed data. So in what we do further, we also use the same technique. So in this case, we can see the 10 events. It was done by Khabotsky et al. In 2021. So we can see the 10 events of loops with, let's say, not that simple damping profiles, which has cannot be directly described by a combination of Gaussian and exponential profiles or exponential damping profiles. And we use exactly the same method without doing anything different. So we use a cutting edge detection method. We assume that we track the points along oscillation as a midpoint between two boundaries of the flux tube. And we detrend it. And then we detrend it, we plot displacements. And then we find the amplitude from it. So similar events. So we take 10 cases, we try to detrend it with same technique. So we use, so it's more or less automatic. You just put the data in and then you do the similar approach to all the cases. And what we obtained at the end. So, and what we obtained at the end, that our model, which incorporates both cooling and resonant damping and loop expansion, can accommodate various observed points. In some cases, it's much better than exponential and Gaussian simple exponential Gaussian damping. In some cases, it's comparable with it. So by considering cooling, we can enhance understanding of damping of transverse King oscillations. And so we have, and then here on this graph, we have both theoretical graph, which is red, for the amplitude for the damping profile of the amplitude. So blue one is red is theoretical graph, blue is observational, and dotted and dash dotted are exponential and damping profiles, and we try to best fit all of them to observe data to see which one could be better in each case. So we've done it for all 10 cases, and in most of cases, considering if one considers cooling effect, they might have better results for approximating the loop, and theoretical model can fit the points better than standard models using exponential or Gaussian damping. So more interesting, we can consider various cooling times. So in previous cases, we considered cooling to be equal to oscillation time, but this could vary. So we can even achieve better understanding we might achieve better understanding of what's going on if we consider various cooling times. So we can consider cooling time slower than oscillation time, or slightly faster than oscillation time, and this will give us different results, and these different results can provide us with different best fit scenarios. So some values will have much less deviation from the observed data. In this case, if cooling time is 3 times oscillation time, we get the results which are the best for this event. But we don't know if the cooling actually happens there, but if we consider it, we can plot such model, and this is not that different from oscillation. Also, the other interesting result is that the amplitude of the total oscillation might relate to the density ratio extracted by the theoretical model. So if we in order to provide best fit, we need to vary the density ratio profile and oscillation time and expansion factors of the cooling loop. So we should see which is the best, and we can see that there is the coronal loops with high amplitude might have lower density ratio in accordance with the theoretical model. And this leaves us with a question, and that if theoretical model could be used as a good seismological tool for coronal loop oscillations, or if we can estimate cooling time not by knowing it or by observing it, but directly from looking at the damping profile. So this is still an open question for us. So for that, there must be a large statistical study in order to see if this is the case, if we can actually estimate the cooling time just by knowing how oscillation is damped, in case it's damped by resonant absorption. Of course, if there are other effects, this model probably wouldn't work as well, since it's only considers resonant absorption in the presence of cooling. So the coronal loop is cooled. So what is the conclusion? So one of the main conclusion of this work is that consideration of cooling might be important for coronal seismology, as it can produce better fits for observed points than Gaussian or exponential combination of Gaussian and exponential models. And then the theoretical model can also provide some seismological estimates for kink oscillation of coronal loops. For example, it can provide us with estimates for density ratios for coronal loop expansion, and then from that on we can find even the magnetic field if we want to, by reversing the equations which are used to find the damping profile via theoretical model. And another thing is that various damping profiles can be accommodated by the theoretical approach. So we don't only need to use standard techniques. So we don't need to be limited by exponential Gaussian, a combination of exponential and Gaussian damping, and just neglect the RAS damping profiles from the picture. We can try to accommodate it with theoretical model. And it would be really interesting to see if at the end the best fit theoretical trend can actually estimate the cooling time. If it could, that we can just estimate the cooling time from looking at the coronal loop seismology without having details on the intensity of the coronal loop. Okay, thank you.
Yeah, thank you. We have a question from Norbert Merja. Have you tried to correlate the infrared cooling episodes with intensity modulations in 171 angstrom?
Nah, that's what I'm doing right now. So I'm trying to do that.
Okay, and we have a question from Richard.
Alex, so when the loop is cooling, you have essentially mass loss from the loop, and that leads to a direct change in the density.
Yes,
this
yes.
Then has an impact upon the periods as well of the oscillation.
Yes,
so I'm
yes,
just wondering if you also looked at the periods in the case where you found these potential signatures of cooling and whether it agreed with whatever amplitude profile you were trying to fit.
Yeah, I also looked in the periods, and it's what was agreeing with the observed periods. I did it. I just haven't showed it. It's you can use the periods as well. The model can accommodate that. So the mass is changing on the top, but we usually look we usually take the variables in the bottom where the parameters in the bottom where the mass doesn't change that much.
Thanks.
Okay. Thank you, Alex. Thank you for your talk. And our next speaker will be Nivet on the topic of understanding the type 2 SPQ contribution to kernel loops. Nivet, please. Alex, would you please stop sharing your screen? Yeah, thank you.
So can you see the screen?
Yeah, yes, yeah, perfect.
Hello, everyone. I'm Nivet, second year PhD student from AMA Observatory and Planetarium, working under Jerry Doyle. First of all, I thank the organizers for this opportunity to present here. Today, I'll be talking about the role of type 2 SPQ in hitting the coronal loops. So this work is done in collaboration with Eamon Scullion, Patrick Antolin, Sere Sahin from Northumbria, and Roberto Susino, Daniel Spadaro, and Clementino Sasso from INAF, and Mihalis from Queen's University. I'll start with a general introduction of the spicules. Spicules are the dynamic jet-like features seen at the solar limb. There are two types of spicule, type 1 spicule and type 2 spicules. Type 1 spicule shows an upward motion as well as a downward motion. Type 2 spicules are very dynamic and short-lived compared to the type 1 spicules. And the most interesting feature is that they disappear without any trace of downfalling matter. Therefore, they are speculated to be the primary supplier of mass and energy to the corona. So, rapid blue shifted excursions, also known as RBEs, they are the on-disk counterparts of these type 2 spicules. So that means in an H-alpha observations, this RBEs appears as a broadening in the bluing of H-alpha with an unaffected red wing. So here is an overview of the CRISP observation in AA 171 CRISP observation. The black box here shows the field of view of the CRISP, and as you can see, the observation is taken very close to the limb and in an emerging active region, and corresponding H-alpha bluing image is presented in the right panel here. This white box here bounds the region of interest in this study. So inside this region of interest, we have a lot of spicules protruding away from the solar surface. So this a detailed view of this region of interest is presented in the right panel here. So the top panel shows the AA171 view, and the bottom panel shows the H-alpha bluing again. And so this region of interest can be divided into two based on its intensity. So the region R1, the bright region, and region R2, the dark region. The white line here separate the region R1 from R2. So the region R1 contain coronal loop food points, and region R2 does not. So this particular field of view provides an excellent opportunity to study the statistics of RBs in a region with the coronal food points and in the region without a coronal loop food points. So to do that, first we need to detect the RBs. So the detection of RB is carried out using residual maps. So an example of a residual map is shown here. So these residual maps are constructed by subtracting the reference profile from observed H-alpha profile. So we get a residual profile in each pixel in the field of view. By taking the maximum of that residual profile, we constructed the residual map. So it looks like this. The residual, an example of a residual map is shown here. So the bright region is where the broadening in the bluing is stronger. Therefore, an enhancement in the brightness can be considered as the location of an RB. So we detected RBs along this horizontal slit marked in yellow, and based on by searching for local enhancement in the brightness. And we repeated this process for every time step and constructed a time distance plot for the RB. So the time distance plot for the RB is presented here in the top figure, and it is overplotted on a time distance plot of the AA171 intensity obtained from the same location. So the red line here separate the region R1 from R2. The blue dot represent the RBs, and the length of this blue dot represent the lifetime of RBs actually. And the bottom panel shows the number of RBE as a function of X location. So as you can see, the number of RBs in the region R1 is much larger compared to region R2. So the region R1 is the contain coronal loop food points. Next, we compared the properties of this RBs, various properties of this RBs, including lifetime and transverse amplitude for these two different regions. So the histograph of this lifetime is presented in R1, presented here, and also the maximum transverse amplitude histogram is also presented here. And we also study the Doppler velocity and the number of times it changed its direction of transverse motion. And we also looked at the distance per sway of the RBEs and the time it takes to complete one sway. So all these properties, and all these properties, an overview of these properties is presented in this table one here. All the properties except the number density are the same in both the regions. So only quantity that differentiate between region R1 and R2 is its number density, the number density of RBs. Next, we looked at the time evolution of these RBs. So based on the wavelet analysis, we see that there is a 4.55 minute periodicity in RB activity, and it is and it's above the 95% confidence level. And at the same location, we obtained the AA171 intensity, and this AA17 intensity also shows a very similar periodicity. It's around 5.10 minutes. And sometimes there is a similar periodicity in both the RB activity as well as in AA171 intensity. And sometimes an enhancement in RB activities appears as a local brightening in AA171 channel. So this indicates the role of RBs in heating the upper atmosphere. We further confirm this via coronal loop simulation performed using Argos 1D hydrodynamic code. So it solves the 1D continuity moment energy equations. And so the basic, so the objective of this simulation is to understand how the coronal loop behave for different energy input. And we also want to know like how the evolution of temperature and density, and finally we also want to compare this model with the observation. So compare the model with observation for different energy input. So the energy input is based on the thermal energy of RBs. So we varied the energy input. We used a range of energy input. For the minimum energy input used in the simulation is suppose we have an RB and only 10% of the RB energy, thermal energy, is converted into heat. So we get 10⁻²². That's the minimum energy used here. And the maximum RB energy is used here is based on the like there are 10 RBs and all the energy is converted into heating. So we get 10⁻²⁴ ergs. We also varied the cadence of these energy pulses. We use 150 as well as 300 seconds. So here is the loop plug properties of all the simulation. Left hand side shows the temperature and the right one shows the electron density for 150 and 300 cadence pulses and for different energy input. So one thing is clear is that like the main feature here is that only for 1.25 into 10⁻25 ergs, the loop plug temperature goes above 0.5 million Kelvin. For other simulation, it does not reach 0.5 million Kelvin above the near the loop lug. And so this 1.25 correspond 1.25 into 10⁻25 ergs corresponds to 10 RBs contributing to the burst. And see, here is the density evolution, temperature and density evolution plot for one of the simulation. So we tried it with two different type of energy input. One for 5.25 into 10⁻23 ergs, and another one for 1.25 into 10⁻24, where there is a 10 RB contributing to the burst. For the higher energy case, we do see condensation development, and only for the higher energy run. And so this condensation cycle repeat with the duration of repeat with the 5.2 hour periodicity. We also in the observation of AA171 data, we also search for this long periodic pulsations. So we were able to see 4.6 hour periodicity in AA intensity in AA171 intensity that is shown here, and it's above the 95% significance level. Finally, we compare the observation with the simulation. So for the 1.25 into 10⁻24 erg simulation, the DEM obtained from the simulation was peaks around 0.8 million Kelvin, and so that means it matches with the observation. For other energy input, it does not reach the 0.8 million Kelvin. So that means a higher energy case with the 10 RBs contributing to the heating matches the observation very closely. And finally, we conclude that the number of RBs in region R1 and region R1 is larger compared to R2, and there is no difference in the properties of RBs in region R1 and R2. Only difference is their number density. So enhancement in the RB activities appears as a brightening in AA171. So this energy input from the RB is significant enough to heat the plasma to 171 temperature. So simulation with the 10⁻²⁴ exocs, that means 10 RBs contributing to the burst, manages to produce the DM peak at 0.8 million Kelvin, which matches the observation very closely. And the condensation developed like the periodicity of this condensation cycle matches also with the EUV observation. So this confirms the role of RBs in heating the upper atmosphere. Thank you. Thank you for listening.
Okay, thank you. And we have time for a quick question. Okay, if there's no question, yeah, if you have any question, you may continue to ask Nivet in the chat box. And thank you, Nivet, for your talk. And yeah, because we are lagging behind, so we have to skip the break. And next talk will be an invited talk by Hui on the coronal magnetic field. Hui, please. I think you're muted, Hui. We can't hear you.
So can you hear me, Jaja?
Yeah. Now we can hear you. Yeah.
Okay, that's good. All right. So thank you for inviting me to this meeting. I'm Hui Tian from Peking University. And today I'm going to talk about magnetoseismology for the solar corona from roughly 10 Gauss to coronal magnetograms. Okay. So, okay. So since, as you know, since 1908, there has been significant advances in the measurement of the solar magnetic field. Based on the Riemann effect, we can now measure the vector magnetic field of the photosphere in the full solar disk with an amazingly high accuracy. However, so far, routine measurements of the solar magnetic field have only been achieved at the photospheric level. So measurements of the magnetic field in the upper solar atmosphere, especially the corona, are extremely difficult. This is mainly because the coronal magnetic field is generally 2 to 3 orders of magnitude lower than the photospheric magnetic field. And such a weak field could only produce very small Zeeman splitting. In addition, due to the very high temperature of the coronal spectral lines are significantly broadened. As a result, the split lines are heavily overlapping with each other, making the measurement of the tiny Zeeman splitting extremely difficult. Because of this, we still don't have a precise knowledge of the coronal magnetic field. The magnetic field couples different layers of solar atmosphere, and the information on the magnetic field of the whole atmosphere is required to understand many physical processes, such as coronal heating and solar eruptions. So the difficulty of coronal magnetic field measurements significantly impedes our complete understanding of the solar magnetism and its interaction with the solar plasma. Magnetic field extrapolations, as you know, are often used to reconstruct the coronal magnetic field. However, these extrapolations are based on assumptions that are not always valid. Also, using different extrapolation methods could lead to totally different results. So eventually, though it is extremely difficult, we still need to work hard to think about how to measure the coronal magnetic field. And in the past 2 to 3 decades, as you most of you know, coronal seismology or magnetoseismology has been widely used for coronal magnetic field diagnostics. And this method makes use of the MHD oscillations or waves that are observed in coronal loops or other coronal structures. From the MHD theory, the observed wave parameters can be used to infer the average magnitude of the magnetic field in the oscillating structures. However, these oscillations or waves are transient events and are just occasionally observed in small regions of the corona. In addition, the inferred magnetic field strength is usually a single number and often around 10 Gauss. For only a few events, a 1D distribution of magnetic field strength was derived. Obviously, their potential for magnetic field diagnostics is limited. So what we need are continuous diagnostics of coronal magnetic field in different parts of coronal structures, which could be achieved if we apply magnetoseismology to more ubiquitous and continuous oscillations or waves in the corona. For example, sunspots are known to show pervasive acoustic oscillations. Combining AIA observations of these waves and magnetic field extrapolations, Jess et al. Has managed to derive a 1D distribution of the magnetic field in a sunspot. But here we focus on transverse waves. At least two types of ubiquitous and continuous transverse oscillations are known to exist in the corona. The first type are the so-called decay oscillations, which normally refer to standing kink waves without obvious damping in coronal loops. These oscillations were first reported by Tongjiang Wang and myself through imaging and spectroscopic observations, respectively. The second type are the pervasive propagating transverse waves in the corona, which were first reported by Steve Tomczyk using HL's COMP instrument. And these ubiquitous oscillations or waves are potentially important for continuous diagnostic of the coronal magnetic field. And in the following, we focus on the propagating transverse waves observed by COMP. The COMP is a coronagraph with a 20 centimeter aperture managed by HLO's Mauna Loa Solar Observatory in Hawaii. Using the iron 13, 1074 nanometer and 1079 nanometer infrared spectral lines, it can observe the solar corona in the range of about 1.05 to 1.35 solar radii from the solar center through imaging spectroscopy and spectropolarimetry. Basically, COMP takes images of each polarization state at several wavelength positions across a coronal spectral line profile. For instance, at 3 different times, COMP takes images of the corona at these 3 different wavelength positions across the iron 13, 1074 nanometer spectral line profile. At each pixel within the field of view, such as the one marked by the red cross, we can construct a spectral profile. So the profile only consists of 3 data points. By fitting the observed line profile with the Gaussian function, we can obtain the line intensity and Doppler shift at each pixel. Then we can produce maps of the line intensity and Doppler shift for the whole field of view. And this movie shows the Doppler shift image sequence obtained from our COMP observation. We clearly see propagating Doppler shift fluctuations almost everywhere in the field of view. Since the Doppler shift refers to the motion along the line of sight, and the magnetic field lines in the off-link corona are largely perpendicular to the line of sight. These disturbances are essentially signatures of transverse MHD waves, most likely kink waves. Our observation clearly showed the ubiquitous presence of these waves in the global corona. And we applied a wave tracking technique to the whole field of view and obtained the global distribution of the wave propagation direction or wave propagation angle for the first time. Because the kink waves propagate along magnetic field lines, the wave propagation angle is essentially the plane of sky orientation of the coronal magnetic field. So we have measured the plane of sky direction of the magnetic field in the global corona through actual corona observations. The wave tracking technique also allows us to calculate the wave propagation speed. This was achieved through the following procedure. And for each spatial pixel within the field of view, we first define a wave propagation track with the length of 31 pixels based on the map of the wave propagation angle I just showed in the previous slide. We then construct a space-time diagram of the Doppler velocity along this track. A 2D FFT is then applied to this space-time diagram, resulting in a K omega diagram. After that, we perform an inverse FFT for the negative frequency part of the K omega diagram, which leads to a space-time diagram for the outward propagation waves. An example of this space-time diagram is shown here. Now from this space-time diagram, we cross-correlate the time series at the center of the track with those at other pixels along the track and obtain the time lag corresponding to the maximum correlation coefficient. Finally, we fit a linear model to the relative position along the track as a function of time lag, and the slope of the fitting is taken as the wave phase speed. We repeated the same procedure for all spatial pixels within the field of view and obtained a global map of the wave phase speed, which is shown here on the left. And we can see that the phase speed mostly lies in the range of 300 to 700 kilometers per second. The uncertainty shown on the right is dominated by the uncertainty in the fitting parameters. which is generally smaller than 40 kilometers per second. A COMP observed both the around 1074 and 1079 nanometer lines. And the intensity ratio of these two lines is sensitive to the electron density in the corona. So they can be used for the density diagnostic. We use the KMT database to generate the theoretical relationship between the line ratio and electron density at different heights in the corona. Why different heights? Because both the collisional excitation and the photo excitation needs to be considered in the calculation. And the photo excitation is largely different at different heights. And this figure shows the theoretical curves for different heights. And here panels B and C show the intensity images of the two iron 13 lines, and panel D is the intensity ratio of the two lines. From the theoretical relationship between the line ratio and the electron density, I just showed in the previous slide, we can obtain the global distribution of the electron density, which is shown in panel E. And panel F shows the uncertainty of the density measurements. Based on the results from wave tracking and density diagnostic, now we can map the magnetic field of the corona. The phase speed is basically the King speed, which is related to the magnetic field strength and plasma density inside and outside flux tubes, as we all know. And in this equation, the subscript I and O represent the parameters inside and outside flux tubes respectively. And in the low beta corona environment, pressure balance is dominated by the magnetic pressure. So the local field strengths inside and outside flux tubes are basically the same. And due to the moderate spatial resolution, which is 7 megameters, COMP cannot resolve individual narrow flux tubes. So the derived density can be regarded as an average of the densities inside and outside flux tubes. Considering this, this first equation reduces to the second one, which is very simple. So the measured phase speed should be the King speed projected onto the plane of sky, and we further approximate the average density in the vicinity of the plane of sky with the derived density. This is actually a reasonable approximation because our measurements are based on the spectral profiles that result from an integration of the spectral line emissivity. Since the emissivity increases with density, and the density generally decreases with distance from the solar limb, the line of sight weight in fact favors magnetic structures in the vicinity of the plane of sky. And forward simulations of propagating kink waves by Magyar and Van Dorsila in the year of 2018 has already demonstrated that this is an appropriate approximation. By substituting the derived phase speed and density into this equation, we can easily calculate the plane of sky component of the magnetic field strength, which is shown here. And the typical value of magnetic field strength in the field of view are 1 to 4 Gauss. The uncertainties were calculated by propagating the uncertainties in the measured density and phase speed, and they are generally smaller than 15% of the magnetic field. We have also plotted the measured electron density and magnetic field strength as a function of height. And the black curves and error bars here represent the measurement results, and the red curves show the power law fitting results. For both the electron density and magnetic field strengths, and this is magnetic density and this field strength, and this active region, this quasar. Okay, so for both the electron density and magnetic field strengths, a larger power law index has been found in active regions than in the quasar, indicating a stronger decrease of the density and magnetic field in active regions. For comparison, we also show results from two density models, the blue and brown lines in panel A and B. And our measured quasar densities appear to be pretty similar to the LeBlanc model. And the density values from the frequently used Nuremberg model appear to be several times larger than those in our measurements for both the quasar and active regions. We also compared our measured current magnetogram with the map of the plane of sky component of the magnetic field from the potential field source surface model. And we see similar distribution of the current magnetic field on the global scale, but distinct differences at scales smaller than something like 200 arcsecond. We plotted the average magnetic field strength as a function of distance or radial distance from the solar center for 4 annular sectors, which are shown in these two panels. And we found a clear discrepancy between the comp measurements and plane and the potential field through surface model results. Some differences may arise because the magnitude of the magnetic field from the potential field source surface model is plotted for a plane of sky slice, while the derived magnetic field from our comp data represents measurement weight by the emissivity along the line of sight. And other differences should be related to the potential field assumption and the use of a synaptic magnetogram in the potential field source surface model. Okay, so here let me briefly mention some possible limitations of this technique. First, our technique, we can only measure the plane of sky component of the magnetic field in the offline corona. And also, the signal to noise appears to be too low in the corona holes, at least from the current observations. Also, our technique requires a continuous observation of for roughly 1 to 2 hours under good observing conditions. And this normally includes 1 hour to observe the transverse waves and additional time for the density diagnostics. So our measurement can not have a cadence higher than 1 hour. And also, our technique cannot be applied to regions affected by solar eruptions because in that situation, the signature of transverse waves will be masked by the rapidly changing magnetic field environment. So what should we do in the future? First, we need to design more advanced chronographs to achieve higher signal to noise and larger field of view, so that we can mirror the magnetic field in the offline corona in a relatively larger region. Also, we need to keep an open mind to explore other methods of corona magnetic field measurements. So, summary. Using comp observations, we have determined the spatial distribution of the plasma density in the corona and the phase speed of the prevailing transverse MHD waves within the plasma. Combining these, we have measured the global corona magnetic field for the first time, and the derived field strengths in the corona from 1.05 to 1.35 solar radii are mostly 1 to 4 Gauss. And these results demonstrate the capability of imaging spectroscopy without polarization measurements in the corona magnetic field diagnostics. So with this technique, global corona magnetic field maps or corona magnetograms could in principle be routinely obtained, thus filling in the missing part of the measurement of the sun's global magnetism. So that's all I want to say. Thank you for your attention.
Okay, yeah, thank you for the talk. We have 2 questions in the Q&A. One is from Tom. How do you disentangle the line of sight integration, which is surely important in the density determination, before the combination with the phase speed? So no line of sight effect.
Well, I mean, almost all offline corona observations suffer from their line of sight integration effect. So this is a common problem for corona observations. Despite of this problem, we still learned a lot from optically seen observations, not only infrared but also EUV, right? In our case, because what we measured is basically a measurement, measurement weight by the emissivity along the line of sight. So if we have a certain structure where the density dominated over all the other structures in the line of sight, then the measured magnetic field is certainly the planar sky component magnetic field in this dominant magnetic field structure, right? If that is not the case, then what we measure is sort of an average, but a weight average by the emissivity along the line of sight. And to have a precise evaluation of this, we think that future forward modeling should also be performed.
Yeah, okay, thank you. And we have another question from Krishna. Considering you have only 3 wavelength points in a line profile, and possibly much larger errors in the density calculations from Chianti, I would expect your magnetic field measurements to have substantial uncertainties, unlike what you show in the plots.
It is true that we only have 3 wavelength positions, but you're talking about the density, right?
Yeah, he was talking about the density uncertainty, and that might lead to more errors in the magnetic field measurements.
Yeah, so the density, we have a detailed discussion of the density of the uncertainty on the density measurement in the supplementary materials of the paper. So if you want to have a detailed look, you can read the supplementary materials. But here I just want to briefly mention that the uncertainty of the density measurement mainly comes from the fitting, mainly comes from mainly come from 2 parts actually. The first part is the uncertainty of the intensity measurement. The second part is the uncertainty of the atomic data. And we evaluated both effects. And I'm not sure why. I'm not sure why you say there might be a large error for the density measurement. I mean, although we only have 3 data points, but basically in the offline corona, I mean, in the absence of solar eruptions, the Doppler shift is relatively small. So we basically can have a pretty precise measurement of the line intensities. I mean, if you look at the profile here, I mean, we're only talking about the intensity, not the Doppler shift or line width.
Yes, hi, thanks. So I was thinking, yes, these lines are pretty wide. These iron 13, 10747, more than 1 from width. And if you have only 3 wavelength points, your Doppler shift should not have larger errors.
Well, I mean, the Doppler shift is really very small. I mean, because we're not talking about solar eruptions, right? In the quiescent corona.
Yeah.
In the quiescent corona, and we're talking about the line of sight integrated corona emission. Yes, in that case, the Doppler shift is usually very small.
Then the uncertainty should be even larger or small.
Well, the Doppler shift is small. What is larger?
The uncertainty on the Doppler shift.
The uncertainty of the Doppler shift. Well, since the Doppler shift is small, and all these 3 sampling positions are around the core of the line or around the center of the line. So in such a case, the fitting result should be more or less reliable. Okay. I mean, yeah.
But these are included.
I agree with you that if we have more sampling positions, then we certainly will have a better accuracy.
Okay.
Yeah, but if you have more sampling positions, more sampling wavelength positions, then you have to decrease the cadence. So if you decrease the cadence, then we cannot perform good measurements of the transverse waves.
Okay. Yeah.
So sometimes we have to reach a balance.
Thank you.
Yeah. Thank you for your question.
I think Robert has a question.
Yeah, hi, Hui. It's nice talk. Maybe it's not a question, maybe, and also I misunderstood, but is it not a bit strong statement that you measure the magnetic field? You are not measuring the magnetic field, right? You're measuring intensity and line profile. So it's not like a Fabry-Perot, right? But you do measure magnetic field.
Well, I mean, if you think about the Zeeman effect, and they are measuring their polarization, right? But people also they measure their magnetic field. It's something similar.
I see. Okay. Thank you.
Yeah. Okay.
Thank you.
Yeah. Thank you, Hui. Thank you for the talk. And,
thank you.
Yeah. Our next speaker will be Mariana on the topic of oscillatory behavior of the magnetic helicity flux. Mariana.
Yeah. Thank you.
Yeah, I can see your screen now. Yeah.
Okay, great.
Thank you.
Sorry, I just should put it. Okay, thank you very much for the invitation, for the opportunity to give this presentation. So this work is dedicated to study the oscillatory behavior pattern of the horizontal and the vertical component of the magnetic helicity flux in the lower solar atmosphere. And our aim is to reveal the different oscillatory behavior in a flaring and a non-flaring active region cases. So we studied the magnetic helicity flux because this is a typical scalar quantity that contributes to the description of the 3D magnetic system at any instant. And this magnetic helicity flux is one of the fundamental parameters which could help to reveal and understand the dynamic evolution of the coronal magnetic field of an active region before a flare occurrences. So in our previous study, we selected 3 flaring and 3 non-flaring delta type active regions. We focus on the delta type active region because they are very often becoming the host of the largest solar eruptions. So in our previous study, which was published last year, we calculated the horizontal and the perpendicular helicity flux term, and also the total helicity flux based on this equation. And in the literature, the horizontal and the perpendicular term very often called as a shearing and emergence helicity flux term. And from now on in this presentation, I also referring to them as a shearing and the emergence helicity flux term. So in our paper, we studied the temporal evolution of the shearing, emergence, and the total helicity flux term during each active region solar disk passage, and we found that these 3 helicity flux components showing a common period, while in the non-flaring active region, they don't have a common period. So basically, this study was carried out in 2 ways. The first direction is led by Szabolcs Sors, who has a poster in this meeting. He's a first-year PhD student, but still, but now he has a very interesting and convincing result where he did the comparison analysis of the 3 helicity flux component on a larger flaring and non-flaring active region cases. So if you are interested, please visit his result here because he's more than take any question from you and give answer during the lunchtime. And the second direction was carried out based on our paper and also based on Szabolcs work. So based on these 2 work, we were inspired us to extend the investigation of the 3 helicity flux component in the lower solar atmosphere. But studying the distribution of the helicity flux of an active region in 3D is not as straightforward as Hui Tian also presented in previously. So therefore, we need to somehow extrapolate the magnetic field, but the literature contains different extrapolation methods with different assumptions. And different method with different assumption can lead us to different 3D magnetic solutions. But luckily, in the literature, we found Dalmasso and other work where they calculated the helicity flux density on a potential field and the nonlinear extrapolation data. And they found that the helicity flux density, which was derived from the different extrapolation method, were highly correlated. And even more convincing result of them is that when they identified the local sign of the helicity flux from the different extrapolation techniques, and they found that these local sign of the helicity flux are very good agreement, almost with more than 85%. And also last year, we applied one of our method on a potential field and nonlinear force field extrapolation data. And even we also found that our method performed much better on the potential field data, like in the nonlinear force field extrapolation. So based on this, we decided the potential field extrapolation should be enough for our study. So therefore, we constructed the 3D solar coronal magnetic field of 14 flaring active regions and 10 non-flaring delta type active regions with potential field extrapolation from the photosphere up to 3.6 megameter. And the grid size in the Z direction was the SDO HMI pixel size. And the temporal resolution of our database was 1 hour. So when we constructed the magnetic field of active region at every moment of time. After that, we calculated the emergence, the shearing, and the total helicity flux term by the so-called D4VM program packages at every 360 kilometers from the photosphere up to 3.6 megameters. And then as a next step, we analyzed the evolution of the 3 magnetic helicity injection rate by Wavelet analysis. So let's see one typical example for the flaring active region cases. This active region produces 1 X-class flares, which is highlighted with these red vertical lines, and the upper panel showing the evolution of the 3 helicity flux component, and the lower panel showing the corresponding wavelet analysis of these 3 helicity flux component. And now we are at the photospheric level as the Z equal with 0 megameter, referring to the photospheric level. And if we look at these 3 wavelet analyses just together, then we can immediately see that the 20-hour period in the 3 helicity flux component. And now let's see what's happening with the periods as a function of height. You can see that the periods are changing, but however, if we focusing first the shearing and the total helicity flux term, we can see that this 24-hour period almost remaining as the largest period from the photosphere up to 3.6 megameter. By in the emerging helicity flux term, this 24-hour period can be observed from the photosphere up to 2.2 megameters, and above 2.2 megameters, the largest periods will be the 30 hours. So let's see the another example for the non-flaring active region cases. Here again, we are at the photospheric level, and you can see that this 3 upper panel showing the evolution of the 3 helicity flux component by the 3 lower panel corresponding for the Wavelet analysis. So I would suggest let's focusing first the shearing and the total helicity flux term. As you can see, the largest period of them is around 25-28 hours, while in the emerging helicity flux term, we can see that within the cone of influence, the largest period is around 15 hours. So now let's see again what's happening with these periods as a function of height. If we look at first the shearing and the total helicity flux, how they are changing as a function of height, you can see that this around 25-hour period remaining the largest period from the photosphere up to 3 megameters. While in the emerging helicity flux, this this 15-hour period can be observed only just from the photosphere up to 1 megameter. So as the next step during our analysis, we decided we are focusing on the identified largest period at the photosphere. So here in these 2 panels, we can see these periods. So on the left-hand side, we can see the analysis of the all flaring active region cases, and on the right-hand side, we can see the analysis of the 10 non-flaring active region cases. So on the x-axis, we can see the NOAA number of the studied active regions. And each active region has 3 columns. The first column is referring to the largest period which was identified at the photosphere in the emerging helicity flux component. The middle bar showing the identified largest period at the photosphere in the shearing component, and the last column showing the largest period at the photospheric level in the total helicity flux component. And again, if we look at together these 2 panels, immediately can see that in the shearing cases, the largest period at the photospheric level of each helicity flux component are quasi-similar in the all flaring active region cases. However, in the non-flaring active region cases, these periods in the emerging helicity flux component are very different compared to the total and the sharing helicity flux component. So from now on, we were interested about how this common periodicity of the flaring active region can be detected. So what is the maximum height where this common period can be still observed? Why is important this? Because the active regions are deeply anchored in solar interior. So if the identified largest period at the photospheric level can be tracked through the solar atmosphere, that it can help to understand or maybe reveal some unique dynamic evolution of the magnetic field structure in the lower solar atmosphere before the flare occurrences. So this color bar showing that, for example, in this case, this 32-hour period can be observed from the photosphere up to 2.5 megameter, or let's see this blue color. You can see this almost 40-hour period can be seen from the photosphere up to 1 megameters. So as a brief summary, so we constructed the 3D solar coronal magnetic field of 14 flaring active region and 10 non-flaring delta type active region with potential field extrapolation from the photosphere up to 3.6 megameter. And in the flaring active region cases, we found that the emerging shearing and the total helicity flux component has a quasi-similar period, which was not in the case in the non-flaring active region. And this common period can be identified through the lower solar atmosphere, which can lead us for a following conclusion. If the horizontal and the vertical component of the helicity flux are oscillating with the same period in a lower solar atmosphere, that means they are building up a coupled oscillatory system, and this coupled oscillatory system has a capability to produce large energetic flare eruptions. However, the horizontal and the vertical component of the magnetic helicity flux are not oscillating with the same period. That means they are not capable to produce large energetic solar eruptions. So this result could be helped to further develop our existing flare and CME eruption models, hopefully in the future. So thank you very much. And I hope I still have time.
Yes, yeah, perfect timing. Thank you, Maria. Any question or comments? Yeah, you may just type in the Q&A and or raise your hand. Okay, if we don't have the question for now, you may ask questions or comments to Maria in the chat box. And Mariana, thank you very much for your talk.
Thank you.
Yeah, and our next speaker will be Richard. His talk will be on the topic of resonant absorption and phase mixing. Richard, please.
Yeah, sure. You see my screen okay?
Yeah, perfect.
Excellent. All right, good morning, everybody. I know it's getting close to lunchtime, people are getting hungry, but I think this is the last talk before the break. So today I'm going to talk about some results that we got from the comp instrument, which seem to suggest that basically resonant absorption and phase mixing probably don't play a key role in energy transfer in the quiet sun. So as Hui showed in his talk, and as we already know, sort of the corona is filled with propagating kink waves. And evidence for this has come from sort of imaging observations, such as those from SDO, and also from these Doppler shift measurements that we get from the coronal multi-channel polarimeter, or COMP. And both of these instruments sort of enable us to measure these kink waves, and it means we really have an excellent opportunity to probe how the kink waves behave at the base of the corona and look at their evolution as they sort of move through the corona. So these waves are kind of pervasive, they're always there, they seem to have a reasonable energy content, and so we're really interested in how these waves deposit their energy into the plasma. And you have to do this by damping the waves, essentially. I'm just going to discuss two possible ways that you can get wave energy into the plasma here, because they're the ones I'm going to focus on in my talk, but there are sort of a number of different other options as well. But one of the most popular ones studied, at least within sort of our community, is resonant absorption. So if you think about that SDO image I showed you of the corona, you have these very thin elongated structures, so either coronal loops or plumes, that are bright in the EUV images, which suggests they're overdense. And so we normally model these features as sort of overdense plasma cylinders. And sort of a realistic one would have a gradual change in density across the cross-section of the structure. And if you have kink waves propagating along this, then in this inhomogeneous layer at the boundary of the structure, you have resonance points where the kink speed will equal the local Alfvén speed. And this essentially allows a transfer of energy from the global kink motion to sort of quasi-torsional Alfvén modes. So this damps the observed kink mode, but it doesn't actually do any heating. You need an additional mechanism to sort of take your kink wave energy and eventually use that for heating. And it's potentially through phase mixing. So once you've excited the Alfvén modes in the boundary of these structures, then the Alfvén modes can propagate at different speeds. You end up with gradients in the wavefronts, and this essentially leads to small spatial scales where the dissipation can eventually occur. So if resonant absorption is playing a role in the damping of waves, then to actually do some heating, it really needs phase mixing to do that. One of the more recent mechanisms for wave heating of the kink waves that sort of come up is this idea of uniturbulence. And it's essentially a nonlinear damping mechanism. So it really kicks in when the wave amplitude is large, but it can be seen as a form of generalized phase mixing, and again depends upon that inhomogeneity perpendicular to the magnetic field, so across that waveguide structure. Okay, so these are kind of the two ones that I'll be focusing on. I guess in the past, the majority of research has focused on the damping of standing modes, okay? And this is, I guess, mainly because that's really what we've been able to observe, sort of predominantly. So from the trace days, we could observe these decaying standing kink modes, and there was a catalogue of events built up from the trace observations, and now SDO has come along. They're very easily seen in sort of AAA data. And again, a large catalogue of these events has been built up by various different people. And this is, well, sort of why I believe the majority of focus has sort of gone through these standing modes. And there have been a number of interesting results. So I'm just showing this plot again that Inigo showed earlier from one of Tom's papers. And it showed there was this relationship between wave amplitude and the strength of the damping. So here we have sort of low amplitude waves down this end, and you see that they have sort of a weak damping, as it were. So this ratio is the damping time divided by the period, and when it's large, that means your damping is weaker. But as the amplitude of the wave increases, you see that this T over P, or tau over P, gets smaller, and you're with a stronger damping. So here there's a potential relationship between sort of wave amplitude and the damping rates that could indicate nonlinear damping mechanisms. And of course, resonant absorption has been looked at as well for these standing modes. So with all this effort going on for standing waves, there's not really had the same attention for the propagating waves that COMP has been able to see so clearly. So Hui gave such an excellent introduction to COMP that I'm going to kind of skip over this, but basically allows us to observe the propagating kink waves at the limb of the sun through the Doppler velocities. So kind of a typical observation in COMP looks like this. You have some coronal loop structure, and you can measure the waves propagating along this path. You can get some Doppler velocity time distance diagram from this, and using Fourier analysis, you can analyze the waves that are in this time distance diagram, and you get this sort of classical star shape in all these observations, which shows the whether the velocity power is, and it's split into outward and inward propagating waves. So those that are moving up the loop leg and those that are moving down the loop leg. And if you've got a keen eye, you can just about make out that the waves propagating down the loop leg, so the ones that have traveled further, have less power than those propagating up from the photosphere. So it suggests that these waves might have been damped on their wave they've been propagating. And what we wanted to do was build up a catalogue of these events, much like the standing wave events that we see, in order that we can sort of begin to probe how the propagating waves transfer their energy to the plasma, or sort of how they evolve as they move through the coronal plasma. So how do we measure this wave damping? So again, this is a velocity power spectra. This is from a paper by R.J. Tawari, and it sort of, I think it shows clearer that damping of the inward propagating waves. You can really see that there is significantly less power of the waves that are returning to the photosphere. And to measure the rate of damping, what you can do is average in the spatial frequency and then divide the power on the from the outward by the inward, and you get a plot that looks like this. And the blue stars are the data points, and you can clearly see there's this increasing trend as a function of frequency, which says that our higher frequency waves are being damped much more than our low frequency waves. So without specifying any particular damping mechanism at this point, you can fit a model that looks like this. So you're fitting this ratio of power, and it basically depends upon this parameter xi, which we're saying is some equilibrium parameter or quality factor, and measures the strength of the damping in this system. So this is how we're going to do it. We're going to take these power ratios from all these different coronal loops that we find in the comp data and estimate the sort of the rate of wave damping through this model. So we were able to build up a catalogue of these comp quiescent loops which showed propagating waves, and we found about 85 quiescent loops, and we were able to fit the damping rates from these different loops. And I just show the results here. So in this light green, these are all the values of this equilibrium parameter that we measured in the quiet sun. So you can see they have quite a large range. I've even clipped the graph here. They go off up to sort of 300 in value. And if you can compare them to the ones you see in active regions from the standing modes, and you see that the values are much larger, typically in the quiescent sun, which really tells you that wave damping in the quiet sun is significantly weaker than what we see in active regions. So what's causing this? Well, we suggested that it was probably due to the density contrast. So if you look at the analytical formula for resonant absorption, where we have our equilibrium parameter here, you can write this in terms of the density contrast. So here this zeta is just the internal density divided by the external density for our waveguide. And if you look at the same or similar formulas for the uniturbulence, you find they also depend heavily on the density contrast. So here we have a formula for propagating waves and one for standing waves. The nonlinear aspect of the uniturbulence comes in through this 1/a factor, which represents the dependence on the wave amplitude as well. So in order to examine how our quiet sun results might depend upon the density contrast, we essentially did a Monte Carlo modeling approach. So using these analytic expressions and some reasonable values for coronal loop parameters, we kind of created a forward model to try and predict what the density contrast would be and how this impacted our equilibrium parameter values, so the rate of damping, using these two damping methods. So on the left here at the top, I show our observational cases, and on the bottom here, I show the results from the Monte Carlo simulations. The key sort of tunable parameter in both sets of simulations was really the value of density contrast. So we had some guidance from active regions, and the density contrast is often found to be on the order of sort of 1 to 5. But using this value, it kind of overfits the data, or it suggests much smaller values of the equilibrium parameter than are actually measured. The quiet sun one, seeing as though we don't have any idea about the density contrast, it's a bit of a free parameter. And in order to sort of find the best matches between the two distributions, where we compared a lot of the moments of the distributions to find the best match, we found that it suggested a much smaller value of density contrast. So only sort of between 1 and 1.25. You can also sort of estimate the relative contributions of both of these mechanisms to the wave damping as well. And that's what I'm showing here. So this is the total damping parameter that we measured, or we obtained from the Monte Carlo simulations. And this is just the ratio of 2. So the larger value suggests uniturbulence is probably predominantly doing the damping, whereas smaller values suggest resonant absorption. So for the standing modes, you see that uniturbulence is likely to play a key role in explaining the damping, whereas for the propagating waves in the quiet sun, you see that resonant absorption is going to be the key contributor to any damping from this. I appreciate I'm running out of time. So why should we expect that we have smaller density contrasts in the quiet sun compared to active regions? And it kind of comes down to the physical intuition of the heating of coronal loops. So during heating events, what happens is you have an energy release in the corona. Energy goes down to the transition region chromosphere and sort of leads to this chromospheric evaporation. In active regions, you have much larger heating rates. Therefore, you can expect significant evaporation of chromospheric material, leading to much denser loops. Whereas in the quiet sun, the heating rate is expected to be much smaller. Therefore, there isn't quite as much energy to do that heating, to lead to the evaporation. And you have much less mass upflow from the chromosphere and transition region. So it's kind of natural that you'd expect smaller density contrasts, and I guess by extension, it's natural that you'd expect the damping is weaker in the quiescent loops. So we find that damping is very weak in the quiet sun, especially when you compare it to active regions. And this really puts severe constraints on wave heating via phase mixing. So if you look at the numerical results of phase mixing, you find that even in active regions, it's not particularly good at combating the radiative losses, right? It doesn't really match them. And that's where it's got a strong damping and a sort of high chance of actually having your waves get to that phase mixing stage. Whereas in the quiet sun, the weak damping leads to less energy being transferred to these quasi-torsional alpha modes, and sort of by extension, less phase mixing. And the reason we suggest for this is that the quiet sun, hence the density contrast, is much smaller in these quiet sun loops. And I'll leave it there.
Okay, thank you. And I think we have a question from Alex. Alex?
Yeah, that's me. This is Alex. So, Richard, have you seen any frequency variation along the propagative wave? Have you observed any frequency variation along?
No, not mainly because we've not looked for it.
Because the recent theory we developed with Ruderman suggests that there should be some frequency variation along the loop for propagating waves in case of resonant absorption. So I'm just wondering if you have observed any.
Well, what we do is we look at the power spectrum. So we convert our Doppler velocities into a power spectrum, and that essentially averages the frequency content over the length of the observations.
Okay.
Really,
okay.
So you wouldn't be able to see it in that method. Maybe if we tried applying some wavelets type analysis, you could pick up some frequency variation in that.
Okay, thanks a lot. Thanks a lot.
Okay, thank you, Richard. Thank you for the talk. Yeah, and our next speaker will be Angela on the topic of direct observational indications of wave-like disturbances in MVP tracks. Angela? Hello, Angela. Can you hear me? Yeah, okay. Angela has a problem with her laptop. So, okay, so maybe we can move her talk to the afternoon session, and we can start our lunch break now. And thank you very much to all speakers in the morning sessions. And in that case, our afternoon session will start 15 minutes earlier. So we will start at 1 o'clock. And and it will be chaired by Chris. Okay, thank you very much, and see you in the afternoon.
Hi everyone. So there were a few technical issues at the end of the previous session, so we've moved 15 minutes early for the afternoon session of the day. Unfortunately, it seems like the previous speaker is still not able to give the talk. So Anne-Marie is kindly offered to start a little bit early. So hopefully that will leave a little bit of time if Angela is available to give the talk later on in the day. So thank you very much for being open to that, Anne-Marie. And without further ado, we've got a packed timetable, so I won't spend too much time talking. Please take it away with your talk.
Okay, hopefully you can all see the slides okay and hear me okay. So thank you to the organisers for giving me the chance to speak to you today. I'm going to talk about helioseismology, and I'm indebted in this work to my co-authors that you can see here. So René Kiefer was a postdoc with us at Warwick until recently, and Katie Cossack, who's doing a PhD with Warwick, and they really did all the heavy lifting with this work. So my talk today is going to be split into two parts. In the first part, I'm going to talk about the excitation of P modes. So these are the internal acoustic oscillations in the sun. And until very recently, it was thought that that excitation rate was constant in time. But in this recent work, we've actually showed that it varies with solar cycle. So hopefully I'm going to show you some results that convince you of that in the talk. In the second part of the talk, as this meeting is all about MHD waves in the solar atmosphere, I thought I'd move to higher frequencies than we normally consider for P mode, so above the acoustic cutoff frequency, and look at pseudo modes. So these are modes that travel out into the atmosphere. And Katie has performed a systematic study of their frequencies and shown that they also vary in antiphase with the solar cycle. Okay, so just very briefly, when I'm talking about helioseismology, we're primarily concerned with acoustic waves of the solar interior. There are thousands of them trapped in the sun. As they travel inwards, they're refracted because of increasing temperatures and pressures. And then they're reflected at the surface because of the sharp drop in density. So they're all confined within a certain cavity, which you can see in this figure over here, but they're confined in different cavities, and it's that helps us to build up profiles of the solar interior using properties like their frequencies. Now, when we describe the modes, we tend to talk about harmonic degrees. So this is just the number of node lines on the surface. And so the lower the number, the lower the harmonic degree, the deeper into the solar interior the modes travel. So the blue line here is a low degree mode, whereas the red one is a high degree mode. And that's an idea that I'm going to come back to throughout the talk. So I just wanted to highlight it here early on. In this talk, I'm going to talk about global helioseismology. So this is considering the sun as a whole, as opposed to local helioseismology, which looks at small patches. But I'm going to talk about resolved data. So this is where we put a spatial filter on the data in order to isolate oscillations of a particular harmonic degree. And the power spectra you can see here are for just one harmonic degree, but we've got a rich spectrum of modes that we can work with. The figure over here on the right is just showing you an accumulation of all the different harmonic degrees, and you can see the ridges all containing thousands of modes. But if we concentrate on just a couple of the modes, as shown on the figure on the left, you can see that they have a structure because they're damped harmonic oscillators. So in order to extract the properties of the modes, we fit Lorentzian profiles like the red line that you can see here. So that tells us the frequency, that if we integrate into the curve, we get power, and the width tells us about how quickly the modes are damped. And what we see if we compare the data at activity maximum and activity minimum is that there's a change. So there's an increase in frequency between minimum and maximum. You can see that the powers drop between minimum and maximum. There's also, it's not quite visible on this plot, but there's also a change in the width of these profiles, so a change in the damping rate. And it's that power and damping rate that I'm going to focus on in the talk, but just to highlight that the frequencies do change as well. They increase between cycle minimum and maximum by around about 0.4 microhertz. That's shown in the black here for Bison data. The red is the scaled version of 10.7 centimeter flux. So you can see that there's really quite good agreement between the two, showing you the solar cycle behavior. Very broadly speaking, the causes come in two categories. So we have the direct effect, which is where the Lorentz force acts as an additional restoring force, and the indirect effect, where magnetic fields would change, say, the properties of the cavity in which the mode is trapped and impact the frequencies that way. So then moving on to the mode damping rates and powers. So in this study, we use GONG, so that's resolved Doppler velocity data. We averaged over quite a large range of harmonic degrees and a wide range in frequency in order to produce these plots. So the left-hand panel over here is showing you the variation in damping rate as a function of time. Whereas where the red is times of pi activity, the black is low activity, and so we can see that there is an in-phase variation with the solar cycle. Over here on the right, we're showing you the mode powers with the same color coding, and what you can see is that the mode powers decrease between cycle minimum and cycle maximum. We can then multiply the mode powers by something called the mode mass. So this is the mass of the solar interior that's impacted by the oscillations. So if you think back to that ray diagram from the start, the low degree modes have a larger mass than the high degree modes. But it's from a model, so it's not dependent on the phase of the solar cycle. So it's unsurprising then that the energies vary in exactly the same way as the powers, which being at a minimum at cycle maximum. If we then combine the energies and the damping rates together, we can get the energy supply rate, which is plotted over here on the right, which you can see shows very little correlation with activity cycle. This is in agreement with previous results that were based on unresolved observations. So these observations are only sensitive to a very small range of harmonic degrees and the lowest harmonic degrees. And that was the state of play when we published this paper in 2018. But because GONG has so many modes, we decided we could do better than this. We could separate things out. And that was really when we started to see a variation in this energy supply rate. So in these plots here, but they're showing the variation in energy supply rate as a function of time, which is on the horizontal axis. The blue colors are showing you higher than average excitation, red lower than average. In the left-hand panel, we've got the mode, the vertical axis is showing you the mode frequency. So what we can see is that there's a variation from lower than average to higher to lower to higher that extends across the entire frequency range. Over on the right, we've got the same plot, only this time the vertical axis is showing you the harmonic degree. Although you can make out the same kind of variation for those intermediate degree modes around L equals 40, 50, it does get very noisy at low and high degree values. It's kind of still, although this is showing you that there is a variation, it's hard to picture whether it's solar cycle related or not. So we've produced some figures that are similar to the ones that I showed earlier. So here we've got the variation in energy supply rate separate only for relatively low frequency modes, separated out into different harmonic degrees in the different panels, the same color coding as in the previous slides. And what we can see is that there's a solar cycle variation in the energy supply rates, with the energy supply rates being lowest at cycle maximum. We calculated correlation coefficients with the 10.7 centimeter flux, and they came out as statistically significant and negative. And what this is telling us is something about the convection. So these modes are excited by turbulent convection in the near surface region. And so it's saying that the magnetic fields are impacting the convection in a way that changes how much the modes are excited. And to me, that kind of makes sense, because we already know, we've known for quite some time that the magnetic fields impact convection. So for example, we've had observations that the convective cells are smaller at cycle maximum, or change in size at least between cycle maximum and minimum. We went one step further when looking at the correlation between the 10.7 centimeter flux and the energy supply rates, and we calculated the cross correlation between the two. What was interesting, so this is shown over in the panels here. We fitted the red curve to the data and looked at the minima, which is indicated by the red dashed line. And what we saw was that it was offset from 0, with the energy supply rate changes lagging behind the 10.7 centimeter flux. What was also interesting here was that the size of the lag varied with harmonic degree. So it suggested that the magnetic field was impacting the modes that are confined to the near surface region first. And we speculate that this was potentially related to inertia. So given the different mode masses for those different harmonic degrees. Okay, so that's the first part of the talk. The second part, like I said, I'm going to talk about high frequency modes above the acoustic cutoff frequency. So what do I mean by the acoustic cutoff frequency? So I've already said that the modes are reflected at the surface because of the sharp drop in density, but they're not all reflected at the same radii. What we see is that low frequency modes are reflected deeper than high frequency modes. And so what we can do is think of this as an acoustic cutoff that varies with radius. So above a certain radius, you don't see modes of a certain frequency. So for example, 0.996 radii and above, you wouldn't see modes with frequencies below 2000 microhertz. And of course, there's a maximum in this that you can see in the red curve over here, around about 5,000, just above 5,000 microhertz. So in theory, modes above 5,000 microhertz are no longer reflected back into the interior. They don't set up standing waves. And so what we should see in the power spectrum is that it's flat. We shouldn't see mode peaks. But quite clearly, from these figures here, we see this series of peaks above the acoustic cutoff frequency in the data. And in the 1990s, Kumar and colleagues proposed a model in terms of high frequency interference peaks. So this is where you get constructive interference between waves that from their excitation point initially travel inwards, become refracted, and then travel outwards, and those that are traveling outwards from the excitation point initially. This figure here is from Kumar's 1994 paper, where it's a little hard to see, but there are two curves on here. The wiggly, the more noisy one is the data, the smoother one is the model. based on this idea, and you can see that there's really quite good agreement there. So this has been the accepted model going forward. And in this model, it means that the frequencies that we see these peaks at depend on both the structure of the sun, but also the position of that excitation. It's been known again since the 1990s that these pseudo modes, as I'm going to call them, vary in frequency with the solar cycle. So this figure on the right is showing you the difference in frequency between cycle maximum and cycle minimum. This region here is the pseudo modes, or this region above is the pseudo mode. So you can see that it's they produce negative shifts. So the frequencies are at a maximum at cycle minimum, essentially. And this has been predicted by models. This figure over here, from Jane and Roberts, where they have an isothermal atmosphere that they vary in temperature and introduce a magnetic field that they change in strength. And you can see that it produces the same kind of shape. But studies of the solar cycle variations of these pseudo modes have kind of been limited to this. There's been no systematic study of how they vary with time, which was what we set out to do with Katie. So our methodology was based on a paper that Renee wrote in 2017 looking at astroseismic data. So we took gong data in the range of L equals 0 to 200. They had 36-day long time series. We isolated the pseudo mode region in the power spectrum. So here we could have gone higher in frequency, but we chose this frequency range because it corresponds to the minimum in that previous plot. So these are the modes that we expect to be shifted most in frequency. We took the power spectrum from the initial time series, so the first one in time that we had as a reference, and then we calculated the cross correlation between the reference and the power spectra from other time series, and that's shown here in blue. We fitted the red curve to the data and took the maximum to be the frequency shift. We then used Monte Carlo simulations in order to get the errors on that frequency shift. And here are some of the results we got. So this panel here is showing you the variation in time for just one harmonic degree. What you can see, the black is then the 10.7 centimeter flux, again, just for comparison. So you can see that the pseudo mode shifts are at a maximum at the activity minimum. What we also thought was interesting was this apparent double maximum. Obviously, we've only found this in one set of helioseismic data at the moment, but it is interesting in that it's very reminiscent of the kind of double maximum that you see at regular cycle maximum in the other activity boxes. Over here on the right, we've got a color map that's showing you the variation in time as a function of harmonic degree, where the yellow are positive shifts, the blue are negative shifts. So you can see that that double maximum exists across the entire range of L that we considered, and there's not a huge amount of variation with harmonic degree. But there is this interesting horizontal structure in the maps, which is something I'm going to come back to in a couple of slides' time. But first, we calculated the correlations with these shifts and the 10.7 centimeter flux. So before doing that, we plotted one against the other. The different colors in this plot on the left are showing you different phases of the solar cycle, of different solar cycles. And so while they don't cover exactly the same range, in shift and 10.7 centimeter flux, there is good mixing, so showing that there doesn't seem to be a cycle to cycle variation. But you can also see that it's non-linear, so we calculated both the Spearman and the Pearson correlation coefficients. So the first thing to notice is that these correlation coefficients are negative and statistically significant. They appear to decrease with increasing harmonic degree. they but there's also this interesting quasi-periodic variation in there, which we believe is related to that horizontal structure that you saw in the previous slide. So to investigate this a little bit further, we took a time slice. We took a few time slices. This is just one example through that color map, and plotted the frequency shift as a function of harmonic degree. And again, you can see sort of a quasi-periodic behavior in there. We calculated a wavelet of this time series. The red and black lines are the 99% significance levels, calculated in 2 different ways. And we can see that there's a significant periodicity that appears to drift in period as we move to higher L. This is unexpected. It wasn't predicted by any of the models. And first and foremost, what we need to do is verify this with other data. So hopefully we'll be looking at the HMI MDI data in the near future. So that's all I wanted to say, but then just to summarize, so in the first part, I talked about mode excitation rate. So contrary to previous results, we found that the rate at which the P modes are excited does vary with time in antiphase with the solar cycle. And remember, this is caused by the convection. In the second part, I showed you that the pseudo-modes do show a solar cycle variation that is in antiphase with the solar cycle. There's this interesting double maximum and periodicity with L, both of which need verification with other data sources. Okay, that's it. So thank you very much for listening.
Thank you very much. Very interesting talk. So there's one question already in the Q&A section, which is from Tom van Dorselaar, who says, how do we need to average the driving power as a function of I and time to obtain the 2018 result?
So I guess that's gone too far. That's this one. So do you mean L and
it could be L and time, yeah.
Yeah. So here we the GONG databases provide the fits to the Lorentz, the parameters of the Lorentzian fits for all L and all M, and so we just took an average, but in each case we looked at different ranges in frequency, so as that we weren't looking over regions where we would expect a huge variation as a function of frequency. I forget the exact frequency ranges because, like I say, they change depending on whether we were considering mode width or from this plot to this plot. The details are in the paper. The reason we do it is because there are relatively large error bars associated with the individual parameters for an individual mode. But because we have so many modes out there, it kind of just makes sense that we average them and because that we're then minimizing the errors for the information that we have. I hope that answers the question.
Okay, thank you. Krishna has his hand up, so I'll allow him to talk.
Yes, hi.
Hi.
I do not understand this, how the magnetic fields are affecting these P modes inside the sun. I mean, also another point I have is that, is there any calculation that how much, obviously the mode mass is higher for the lower L modes, but they might be less affected by the field or something like that. Is there any calculation?
Yeah, so when we do the frequency shifts, for example, we would normally normalize by this mode, by mode inertia actually, which is dependent on the mode mass. And so if you don't do that, you see that the higher L modes are affected more than the lower L modes. So there's definitely that variation in there. So yeah, in terms of the mode frequencies, as I said, you've got the Lorentz force and changes in the say it could be change in the stratification of the cavity that causes this variation, and that variation it's still a little bit woolly, a little bit hand wavy. We've done some simulations, but in general, at the moment, we need larger magnetic fields that are reasonable in order to replicate these kind of shifts. So work is still going on there. In terms of the mode damping rates, again, you would expect the magnetic field to increase the damping because it's an additional restoring force. That damping, if you increase the damping, then I guess it's understandable that you see a decrease in power over a certain amount of time. And that's kind of why it was always assumed that this energy supply rate is approximately constant, in that those two cancel each other out because it's the same effect. What we think we're seeing now is that there's an additional impact here, that there is less excitation. Again, we've only just found this result. I think what we ideally need is some sort of models or simulations to see how reasonable it is. In my mind, though, the fact that we know that the convection varies through the solar cycle, it seems reasonable that will then have an impact on excitation, but actually quantifying the cause beyond that, we haven't looked into yet. So if anybody knows of a way that we can model this, is familiar with these kind of models, I'd be happy to work with people on this.
So this cavity you're talking about is the subphotospheric magnetic cavity, which is pretty much close to the surface, right?
Yeah, absolutely. Yeah. So we know from what we see certainly for the frequencies that we're talking about something that's near surface. It's less clear for these results, but we know from the helioseismic results that the modes are excited in very close to the surface as well. So it would seem reasonable that it would be a near surface magnetic field.
Okay, thank you very much.
Okay, so thank you very much.
Okay.
Very interesting talk. So next up, we have Joseph Scalisi from the University of Sheffield, who's going to be talking to us about torsional alpha pulses in zero beta flux tubes. So Joe, if you'd like to share your screen. Yep, everything looks good. So please take it away. You might be muted at the moment.
Hi, yeah, sorry about that. So you can see the screen now. Sorry.
Yes, everything's on the screen. Thank you.
Okay. Yeah, so I'm Joe Scalisi. I'm a second year PhD student at the University of Sheffield, working with Robertus, and I'll be talking about torsional alpha wave pulses. So first of all, a bit of context. So spicules and other solar jets, of course, can transfer significant mass and energy. So they are likely to contribute to coronal heating and the solar wind. In fact, their total mass flux is estimated at around 100 times that of the solar wind. But their underlying mechanisms are still not quite fully understood. So, and then we have magnetic bright points, which are intense magnetic regions, which are concentrated along intergranular lanes in similar regions to the spicules as well. And we can model these as magnetic flux tubes. So connections between these features have been suggested. For example, torsional Alfvén waves have been observed in both spicules and magnetic breakpoints. So what we want to do is to mathematically analyze these features, specifically the effect of a magnetic perturbation on plasma in a flux tube. So analytical models complement numerical simulations and observational data to help us get a more complete understanding. So onto the model. So we have developed an analytical flux tube model, which you can see here, with a vertical background magnetic field. And yeah, and we use the regular perturbation method. So the parameters are defined with this functional form, and we have the small perturbation terms here. This is just a small parameter, this epsilon. So the model has a boundary condition at the base of the tube, which looks something like this animation down here on the lower right-hand side. So the waves are introduced via a shear perturbation. And then from the ideal MHD equations, we get this wave equation for the theta component of the magnetic field. And we consider solutions propagating in the positive Z direction. And this is to simulate the Alfvén waves which propagate from the photospheric level upwards into the chromosphere. So this approach allows us to begin to look at the nonlinear effects of these perturbations, including the effect of the Lorentz force on the plasma, particularly this vertical component here, which may be able to drive plasma in jet-like motions. And then we simplify the model using the zero plasma beta approximation, which should be consistent with the intense magnetic environment of a magnetic breakpoint. So where we expect magnetic forces to dominate pressure forces. So onto the results. So so the torsional perturbation results in vertical mass flux due to the Lorentz force, as we expected. And you can see here we've used an example solution in the form of this propagating wave pulse to illustrate the mass flux. So this is just a rescaled representation of the pulse with you can see the shear perturbation at the bottom here, and the brighter yellow is greater mass flux. So the pulse propagates at the Alfvén speed, which is typically around 10 to 20 kilometers per second in this context, in the vicinity of a magnetic breakpoint in the lower chromosphere. And at this speed, the pulse reaches a maximum vertical extent of around 3 megameters within 150 seconds. And so approximately this matches the properties of solar spicules that we've observed in the early stages of their evolution, which is a good result. So yeah, so some discussion of this. We can only estimate the magnitude of the mass flux, unfortunately. However, even a small amount of plasma lifted from the chromosphere lifted from the photosphere would be significant in the chromosphere. More observational data will be useful for a better comparison of this. So the intended focus of this research was to look at jet formation, but we would also like to model the full evolution of a jet. But this solution is only applicable to the initial formation because we still need to account for how the solar atmosphere changes with height, etc. So, and it may also be that this mechanism is more applicable to certain types of jet, such as type 2 spicules, which tend to fade away instead of falling back down. So originally we used a fully nonlinear model without the zero beta approximation. And we found that the results from the simplified model that we just seen were compatible with the more complex model and were consistent with the physical system. But we were able to avoid some of the problems involved in the complex model. And currently we're working to more accurately model the physical properties of other jets and the solar atmosphere in general by including wave reflection and atmospheric stratification. And we're also collecting observational data for comparison with our results and to look at different classes of jets as well. For example, this one here is a macrospicule that we've observed in some previous work. Yeah, so a quick summary. So we studied the effects of torsional alphane waves in the context of spicules. And we've developed an analytical model using the regular perturbation method. We found that this may result in a secondary perturbation and may result in vertical mass flux, and that this should be consistent with observed properties of spicules. And here we've just got the paper detailing this work, and then we've also got another paper which is deals with a similar problem but in slab geometry. Yeah, that's about it. Thank you for listening.
Okay, so thank you very much, Jeff. So we have two questions in the Q&A. The first from Tom van Dorselaar again, who says, you say that this model is relevant for the first phase of the spicule trajectory, but afterwards spicules fall down basically to the ballistically to the solar surface. Why do the alpha wave and nonlinear density front decouple after they reach the top of the spicule trajectory?
Yeah, that's a good question. That's kind of what we're working on now. We're looking to account for the fact that the spicule should fall back down to the surface, which is why we also said that it accounts for this one accounts for the initial phase. So yeah, that's kind of a limitation of the model, and this is something that we're working on overcoming.
Secondly, we have Norbert Magyar, who says, if spicules would be generated in such a way, one should see strong Doppler signatures when looked at spicules sideways. Is something like that observed?
Again, that's a good question. I don't know much about the observational side of that, but hopefully that's certainly something we'll look for. Sorry, I can't offer more interesting insight into that.
Thank you. And Alex has his hand raised, so I will allow you to chat. Hopefully you are allowed to talk. So Alex.
Hello, can you hear me?
Yes.
Yep.
Great. So my question is, how do you model the density? Initially, when you showed some modeling on the theoretical model of the spicule, what happens to density? Because I haven't seen density there at all. So is it like a constant or a function of something?
Yeah, in this case it's just a constant.
Okay,
yeah,
okay.
it's quite...
So you don't consider any stratification of it.
Yeah, again, that's the next phase of the model.
Okay, okay.
But yeah,
thanks.
And that's what's constant. Thank you.
Thanks a lot.
Okay, so thank you very much, Joe.
Thank you.
Okay, so next we have Krishnaprasad from the Indian Institute of Technology in Varanasi, who is going to be talking to us about standing MHD waves in magnetic annulus geometry. So if Abhinav, you'd like to share your screen, that's brilliant.
Yes, so is it visible?
Yes, everything's ready. So thank you, take it away.
Okay. So myself, Krishnaprasad, and I'm a master's student at Indian Institute of Technology, Varanasi, currently doing my master's under Dr. Abhishek Srivastava, and I'll be discussing some of the initial results from one of the projects we are currently proceeding with. So basically, we are working on the standing MHD waves in the magnetic annulus geometry, and I've been working on this project in collaboration with Professor Robertus. So a quick overview. So we'll be introducing as to the topic, then we'll discuss the theoretical model and some of the approximations that we are considering, and then the final discussion and conclusion. So basically the magnetic confined configurations in the solar atmosphere, such as the coronal loops and the dynamic flux tubes, subphotospheric tubes, are basically an important aspect of the solar magnetoseismology. And for a long period of time, they have been extensively studied through a variety of models. And in 2002, Ruderman and Roberts suggested that the flux tubes to be the implementation of basically a thin inhomogeneous layer in the flux tubes, which can explain the observed damping of the coronal loop oscillations. So basically what we are trying to do is basically develop an analytical model for these standing wave modes in flux tubes. And we build upon some of the previous works which have dealt with the magnetic annular structure. So starting with the basic theoretical model, we have basically a cylindrically symmetric flux tube with 3 different regions. And basically the regions are divided in a stepwise fashion. So we have distinct densities in the inner core, the annulus, and the exterior region. Then we have the straight longitudinal magnetic field in all the 3 regions. And the pressure is accordingly stepwise distributed. So we begin with the linearized set of MHD equations. We have considered the incompressible plasma limit, as well as we are considering the ideal MHD equation. So we have the momentum equation, and we have the induction equation and the incompressibility condition. So we have written the equations in terms of the Lagrangian displacement, and we have the total pressure perturbation accordingly in the momentum equation. So basically we use these set of equations to derive a dispersion relation for the standing wave modes. And for that, we accordingly define the set of boundary conditions which can trigger the standing wave mode. So for the annular geometries, which we have a cylinder which is fixed between z equal to 0 to L. So we have a fixed length for the tube. And considering the appropriate boundary conditions where the plasma is static at the endpoints, so we have Lagrangian displacements to be 0 at these endpoints. Further, the flux bundle is having the constant magnetic flux. So the magnetic perturbation is accordingly 0 at the endpoints. And finally, we have the pressure perturbation conditions at the endpoints so as to not further instill any motion into at the endpoints of the tube. So these set of boundary conditions, using these set of boundary conditions, we try to study the standing modes which are being generated in the annular flux tube. So in order to satisfy these boundary conditions, we have a similar set of Fourier solutions which were followed by Oxley, Samberger, and Erdelli. So we have the Lagrangian displacements in the cylindrical coordinates, we have the total perturbation, and the corresponding wave number is decided based on the loop length. So we have based on the value of n, we have the fundamental and higher order harmonics. And the basic perturbations are these set of Fourier perturbations satisfy the boundary conditions, the line tank boundary conditions. So we substitute these set of Fourier solutions into our basic linearized MSD equations, and we have the final total pressure equation. And further solving this set of equations in the three regions, and further considering that the Lagrangian displacement as well as the total pressure is balanced in the three regimes. So we finally obtain the dispersion relations, which was also previously derived by Carter and Ederle in 2007. So here the K and I are basically the Bessel functions, the mth order Bessel functions. So equation 13 is the general dispersion relation for the annular geometry. And we basically are going to exploit this dispersion relation to analyze the period ratios and further standing modes. And in order to solve this dispersion relation, so we consider a set of approximations in order to simplify it. So we have the weakly homogeneous and the thin annular approximations. So following a similar approach, which was considered for the asymmetric slab case in Oxley, Zamberger, and Ederle. So we defined two set of parameters, which, so first we have the epsilon, which basically talks about how the annular width distributed is the magnitude of annulus width in comparison to the length of the tube. And secondly, we have the tau parameter, which talks about the inhomogeneity of the annular region in comparison to the core of the tube. So these two parameters are basically being utilized to simplify the dispersion relation in order to further solve it. So under the thin annular and weak homogeneity approximations, we consider the order of epsilon and tau to be smaller. And we simplify the dispersion relation 13 using these approximations and including higher order terms in epsilon and tau. So the coefficients of the quadratic expression have been solved after a lot of algebra. Unfortunately, I could not show these expressions here due to their large size of expressions, but surely will be this. So here basically we have solved our dispersion relation, general dispersion relation for a set of conditions, coronal photospheric conditions. So basically we have assumed that the Alfvén speed in the inner core of the tube is much larger as compared to the external. And for simplification, the densities in the three regimes have been considered to be the same. And further, we have in the top, basically the left-hand side panels are plotted for the sausage mode, whereas the right-hand panels are plotted for the kink mode. So basically, in the annular geometry, we have two sausage and two corresponding kink modes. So the top panels basically show the period ratios of the fundamental and the first excited harmonic in relation to the epsilon parameter, whereas the bottom panels show the period ratio in comparison to the tau parameter. So basically here we can see that for there is in each of the cases, there's one single mode which has a constant period ratio of 2, whereas there's for the sausage modes, we have a second mode which has a period ratio lesser than 2, slightly lower than 2, whereas for the kink modes, we have a different mode which has a period ratio higher than 2. And here we can also see that the top in the tau parameters which we have considered, so they are basically negative. So since the magnetic field in the annulus region is taken to be lesser as compared to the inner core. In the top two panels, basically, we have taken the A by L ratio of the flux tube to be 0.01. Basically, it's a thin tube, and whereas in the bottom panel also the A by L is 0.01. And here also we show similar set of curves. So basically the left hand is for the sausage mode, whereas the right panel is for the kink mode. So here we show the variation of period ratio in comparison to the A by L ratio of the loop. So here we can see that both these panels are basically plotted for an epsilon of the order of 10 power minus 4 and similar order for the tau parameter. And the tube conditions are accordingly similar, with the inner core magnetic field to be larger as compared to the external. So for the sausage mode, we have a particular mode with period ratio exactly 2, whereas we have a second mode which has a decreasing period ratio up to 1.9. Whereas for the kink mode, we have a similar mode which has a period ratio of 2, and the other mode has a period which increases slightly from 2, reaching close to 2.05. So further moving to the thin tube approximations for the dispersion relation, considering that the Ka and Kr to be less than 1, we can approximate and simplify the dispersion relation as below. So for the sausage mode, we have equation 17, and for the kink modes, we have equation 18. So these are the set of equations which have been previously also mentioned in the work of Carter and Daly. So they have been derived under the thin tube approximation. And on these set of dispersion relations, we further apply the thin, annulus, and weak homogeneity approximations. And based on that, we obtain the further set of dispersion relations 19 and 20. Here also the set of coefficients have been obtained after a lot of algebra and manipulation. So what we do is basically we try to understand how the period ratio is going to change, or we understand the period ratios in these set of approximations, the thin tube approximation. So here we show the thin tube approximation case for the sausage mode, and we can see that the period ratio, it shows a similar variation as for the general case. So here we have in the left panel, we have the period ratio in comparison to epsilon, where we have chosen the A by L to be 0.01. So here we have a single mode of period ratio 2 and a second mode with period slightly lesser than 2. And similarly, here we have the variation of period ratio with tau and A by L as well. So we can see that in the sausage modes, the period ratio basically reduces for a single sausage mode, the period ratio reduces slightly from 2, lesser than 2. So whereas there is one mode which has a period exactly equal to 2. And all these panels are also plotted for the similar set of tube conditions where the inner core magnetic field was larger as compared to the external field. And then we have also explored the wide tube approximation cases. So considering that Ka and Kr to be much larger than 1, we can similarly approximate the general dispersion relation under this wide tube case. And further, we apply the thin annulus and weak homogeneity conditions. We obtain a final 8th order dispersion relation in omega. And here also the coefficients have to be solved after much of algebra, and they were algebraically solved on numerical softwares. So here we can see we have basically plotted the solutions of the wide tube approximation case, and the basic set of tube conditions are similar as before. And for all the, however, here we have for the top 2 panels, here we have considered the A by L ratio to be 10 basically. So basically the tube radius is wider as compared to its length, and the epsilon and tau parameters have been varied accordingly. So here we can see the 4 set of solutions which we have obtained from the dispersion relation. And in the bottom panel, we have plotted the period ratio with respect to A by L, and here we have varied A by L from 10 to 100. So we can see that like in the general case, we saw that the period ratio was largely varying with respect to A by L. So it varied up to 2.05, but here we can see that the period ratio doesn't vary much in comparison to the A by L ratio for the wide tube approximation case. And some final discussion. So basically, we have developed a model for the standing MSD waves using the line time boundary conditions. And further, we have solved these set of dispersion relations under the thin annulus and weak homogeneity simplifications. And we have also explored the thin and wide tube approximations for a better insight into the wave modes and its applications. And further, we basically plan to develop this model and analyze the period ratio for different set of photospheric and coronal conditions. Although this model would be much more applicable for the photospheric cases, since for the sausage modes specifically, but for the kink modes, this is applicable for a wide range of solar atmosphere. So we wish to explore the period dependence of period ratio on the tube radius as well as the epsilon and tau parameters. Further, we also wish to develop this model by changing the overall background conditions of the loop by considering a twist in the magnetic field in the annulus region, similar to the work on propagating waves done by Carter and Daly. So thank you for your attention.
Thank you very much for the great talk. Does anyone have any questions? Oh no. If not, thank you again, Avanal, for the great talk. And we'll move on to Rajab Ismaili from KU Leuven.
Yes. Hi, everybody. Thanks so much for giving opportunity to represent my work. So I hope you can see the screens.
Yeah, everything's there now. Thank you. Take it away.
So my name is Rajab Ismaili. I'm second year of my PhD at KU Leuven. I'm working with Tom van Durselaar. Today I will talk about the properties of unit turbulence in incompressible MHD. Yeah. First of all, I would like to give a short introduction. Firstly, about the MHD turbulence. So due to the convection motion that they perturb the magnetic field, which launches the waves upwards. And as this wave travels upwards, reflection will happen. And the wave energy will reflect downward, which is like towards to the sun. And this reflected waves essential to the alpha wave turbulence, because what will happen as these waves will interact each other. So the waves moving out of the sun or upward will interact with the waves which is reflected back, and it will lead to the turbulent cascade and leading to the energy dissipation, as you can see in the figure as below. So as a summary, I should say like the main idea was in earlier studies that the two contrapropagating waves should generate the turbulence. And the small scale structures are generated by the wave collisions. And in earlier studies, they were considering the either completely homogeneous background or only inhomogeneity along the magnetic field. Later on, the series work by Magyar, Van Durselaar, and Gussen from 2017 and then 2019. So they consider the main difference was that they consider inhomogeneity across the background magnetic field. And alpha waves now propagates along or against the magnetic field. And this generates turbulence, which is termed uniturbulence because it's generated by the unidirectionally propagating waves. And these waves, which carry both associative variables, z plus, z minus, it's just combination of flow and alpha speed, which is very important of study of MHD turbulence, as it represents the alpha waves. And in the figure below, we can see it's the same figure as before. Here's the only difference that the wave packets, they propagate parallel to the magnetic field, but the background flow is inhomogeneous across the field, and which is leading to the self-deformation of alpha waves. And later work by Van Durselaar et al. In 2020. So they reformulated a well-known King mode solution for transfer waves into the associative formalism in a cylindrical flux tube. They calculate this for standing waves and for propagating waves. And they also calculate the damping time for the energy cascade rate by taking the ratio of average wave energy density over the average of energy cascade rate. And they found this beautiful equation, which is here shows the tau as a damping time. You can see that it's inversely proportional to the velocity amplitude, to the density contrast, which is the ratio of internal density to the external, and also to the radius. Here they consider cylindrical. So this was done for the cylindrical case, which has difficulties for numerical verification. So one of the main aim of our work was that to check the simplified case in a planar geometry, if it matches with the numerical simulations. So we started with the incompressible MHD equations. We take a equilibrium geometry in Cartesian coordinate. We take a magnetic field along the z-axis without background flow, and we take the piecewise constant density as the upper part is rho r, like heavier than the lower part for density. So you will have the second order differential equation for this case, which is easily solvable, and you will get this solution. And implementing the continuity conditions for total pressure and the displacement, x component of displacement, you will get a known dissipation relation for the surface waves. So in order to calculate the SRC variables, we determine the linear variables as here. And the SRC variables, to calculate the SRC variables, we also take the total pressure as a propagation wave in this formula, and we calculate all the three components of SRC variables as follows here. And later we calculate the energy dissipation rate for upward and downward surface Alfvén waves, which is given in terms of the SRC variables here, as well as the wave energy density expression. We calculate for the left and the right side for our solutions. And the main idea to showing these formulas that when we calculate the average value for energy dissipation rate, you see that we have a cubic, the third order of the time. So when you integrate over the time, you will get 0. So that's why we use root mean square for energy cascade rate. This is the calculating the energy. We calculate the energy density average over the cross section and over the period, as it also mentioned in this paper, and also average of energy cascade rate, but the root mean square approximation. And we get the damping time expression for energy cascade by taking the ratio, again, the average energy density over the average energy cascade rate. When we obtain this formula, and to simplify this formula, we use the long wavelength limit. We introduce new parameters, which is means the ky much bigger than the kz. In other words, we could say it's a quasi-perpendicular propagation, a quasi-perpendicular approximation, and it yields to this formula, which is similar to the paper and the equation I showed in the beginning. And also we got the result that our damping time is inversely proportional to the velocity amplitude, wave number, and the density in contrast. So to compare to our numerical model, theoretical model with a numerical simulation, we use these the ideal MHD equations using the code MPR MRWAC. Our domain size is 0.5, 0.1 in y direction, and in z direction we change it because due to the changing the density contrast, the damping length, it gets smaller or bigger, and I will show in the further cases as well. And so the base resolution, I took the 60-60-40 with 3 levels of refinement. We take upper boundary conditions in x direction for all variables, periodic boundaries for the y direction, and at the bottom of z direction, we used the sinusoidal velocity driver as it's formulated here, and at the top of the z direction, we take the open boundary conditions. We take homogeneous magnetic field, and then we change the discontinuously, varying the discontinuously of density at x equals to 0. That's figure you can see here. I put this figure as well to show how the velocity driver is perturb our interface. So we consider in total 9 simulation, which is in this figure you can see. We have like we take velocity amplitude value for 0.06, and for this value we compare we take 5 different density contrasts, which is 1.1, 2, 5, 10, and 20. And similarly for density contrast, which is this case, when it's equals to 5, the ratio of this, we take 0.1, 0.3, 6, 12, and 18. Here's the main simulation for the density contrast at z equals to 5 and amplitude 0.06. So the picture taken at the half of the domain at cross section at z equals to 0.5. We can see that already deformation appearing on the density surface and indicating the nonlinear generation of smaller scales. And here, that's the total simulations that we have, different velocity amplitudes for zeta 5 different simulations, and also 5 different simulations for density contrast, which is showing the turbulence energy loss from the large scale motions to the small scale motions, leading to the cascade as well. So in order to analyze our damping or cascading, so we take these widths, which is the interested part. We take the Vx component in the y direction, at also in every cross section, at every time step. And we do the Fourier analysis in y direction, and we compare this with the exponential profile. So what we do, as in this figure shown here, so this is the power amplitude of fundamental mode in the driver frequency, which is given, and this is, you see, it's decreasing, and which means the development of turbulence and same like energy loss from the large to the smaller scales. We follow these peak values of the first wave, for example, and we take the we find the exponential with this profile. We get our damping length. You see the value is here, and then with this value we calculate the damping time, and we compare our results with the theoretical model that we have. And so here is the damping time versus the density contrast, 5 different simulations. Here's red square means the first wave that I was following. And then I also took the average of the first 5 waves, which you can see here, that there's waves are because of the driver is moving. And so we also take the first 5 waves average, and we see that it's the damping time, it's the numerical simulation match with our theoretical almost perfectly, and we also calculate for the velocity amplitude similarly. So as a summary, plasma homogeneity leads to the turbulence. We constructed analytical model for unit turbulence evolution in surface Alban waves. We found the expression for damping time, which is also we compared to the Van Durseler et al. 2020 paper that they did for the cylindrical case, but we did in the planar case, and we got almost similar result, except the factor is different. And we analyzed the numerical models with compared to the analytical model, and we proved our theoretical model. Thank you so much for your attention.
Thank you very much for the interesting talk. We have one question already in the Q&A from Alex Shukovatsky, who says, how strongly the choice of velocity driver affects the simulation?
So we also consider velocity driver with exponential profile, but we almost got the similar results as a surface waves that with exponential profile kappa x, and we almost get the similar results. So I think not very strongly it's affecting.
Okay.
But yeah.
So thank you. Is there any further questions? If not, thank you, Rajab, again.
Yeah, thank you so much. Yeah.
And next we have Noemi Sandberger from the University of Sheffield, who's going to talk to us about asymmetric waveguides in the solar atmosphere. So if Noemi, you'd like to share your screen.
Yeah, hopefully it's working. Hi.
All right, we see the screen. It's not in full
Great.
screen mode, but
Yep, should be now.
Yep, that's right. Thank you. Take it away.
Oh, sorry. So, hi, good afternoon, everyone. I'm Noemi Jamberger, a PhD student at the University of Sheffield, working on the reverse survey. And I'm going to give a brief summary of some of the studies we've done about asymmetric waveguides in the solar atmosphere recently. Firstly, a bit of motivation for the whole topic. So in solar magnetic seismology, we want to obtain diagnostic information about the solar atmosphere by building simple theoretical models and then taking observational data about background parameters of certain solar features along with wave properties, and using these, solving an inverse problem to draw conclusions about quantities in the solar atmosphere that would be difficult to measure directly, such as magnetic fields. Luckily, many features in the solar atmosphere can be approximated as magnetic slabs. And since the atmosphere itself is gravitationally and magnetically highly structured, incorporating asymmetry into our slab models it seems like a good way to start more precisely describing this whole variety. Well, the process of generalizing the slab model goes back to the classical symmetric slab models described in a series of articles by Roberts and then Edwin and Roberts. And building on that model recently, Matthew Alcock in Sheffield described wave propagation in a magnetic slab that was placed in an asymmetric magnetic environment. Non-magnetic environment, and later used this model to identify wave modes and find Alfvén speeds in chromospheric fibrils, for example. The next step, building on this, was adding asymmetric magnetic fields to the external regions as well. And from then on, you can see that by now there's a whole growing family of asymmetric slab models, each of them suited to help interpret and diagnose different solar features. For example, both of these, the externally non-magnetic and magnetic cases, were examined for standing waves as well, and which could be expected to see, for example, in light bridges and prominences. And actually, if we go back to light bridges, we can also look at them as a series of multiple slabs, while them and the umbral cores, they are embedded between. So we're at this model, which was described by Daria Shkopotskaya. And so far in this top half, all these descriptions were static, but we can also add bulk background flows to the models, which was first done in the asymmetric case by Mihai Barbulescu. And he used this model to examine a CME flank region in detail. After that, building on what he's done already, I've started studying an externally magnetic asymmetric slab with asymmetric background flows in the external regions, which could serve to model MBPs somewhat better. And if we generalize everything a bit further, all three regions can have different densities, pressures, temperatures, magnetic field strength, and even flows as well. For example, you could expect to see this in the penumbra regions. In general, for each of these models, we start by writing up and then linearizing the ideal MHD equations, which express the conservation of mass, momentum, magnetic flux, and energy, respectively. then looking for plane wave solutions in these slabs, and making sure that on these interfaces, the total pressure and velocity perturbations remain continuous. And using these techniques, we can derive a dispersion relation, which is then specific to the chosen waveguide properties. On this slide, I've got the dispersion relation for the asymmetric magnetic slab written out more in detail. But for this one, and even for other members of this whole slab family dispersion relations, it's true that they incorporate the characteristic speeds, so sound speed, off-beam speed, and tube speed in each of these 3 separate regions, as well as the density ratios between them. For this model specifically, it's a slab comprised of 3 different regions of magnetized plasma. Each of them can have different densities, pressures, temperatures, and magnetic fields, as long as they remain in total pressure balance. And for this model, the slab extends infinitely in the y and z directions. So going back to the dispersion relations, it's also a common property between asymmetric dispersion relations that, unlike their symmetric counterparts, they don't decouple into 2 separate equations. So now we only have one single equation which will describe both sausage and king type oscillations, which in turn will also look asymmetric and have mixed properties. As you can see on these videos, what they would look like. They were made with the case of the non-magnetic environment. And a number of videos like this is available on the SWAMP website to illustrate how these so-called quasi-sausage and quasi-kink modes behave. And the eigenmodes of asymmetric slabs can, of course, also be classified as surface or body waves, where surface waves are evanescent outside and inside the slab as well, and body waves evanescent on the outside but remain oscillatory on the inside. So now we've set up the basic. I'm going to focus more on the applications. We've looked at the most cases for the asymmetric magnetic slab. So that's the one I'm focusing on now. There are 3 main groups of applications. One of them pertains to the slices of the global layers of the solar atmosphere. Firstly, we can look at the segment of the high beta photosphere, the low beta corona, as an asymmetric magnetic environment, and imagine in so-called interface region made up of the transition region and the chromosphere in between them as a region that serves as the slab and is described by an intermediate value of the plasma beta. We can zoom in on this model a bit and improve it, and look at the chromosphere, the transition region, and the corona as a slab system, where the chromosphere has an intermediate beta value. The corona is, of course, low beta. They serve as an asymmetric environment for a slab that is the transition region. Then there are applications, potential applications to large-scale local features, such as coronal hole boundaries. Here, the boundary region serves as the slab itself, and it's surrounded by an asymmetric environment, which is made up of, on one side, the coronal hole, and on the other side, a quiet sun region. Another potential application is prominences, which we can look at as cooler, denser slabs in between 2 low beta, hotter coronal regions. And finally, I've come to the small scale local features that this model can be applied to. I'll talk a bit more in detail about these ones. So one of them is light bridges or light walls. These phenomena appear as a brighter band between 2 umbral cores in sunspots, and they form areas of partially restored convection and weaker magnetic fields generally. And since they are embedded in between 2 different umbral cores and they are quite elongated, we can look at them as asymmetric slab systems. So working within the limits posed by typical speed values in the literature, we investigated various possible descriptions of a light bridge as a magnetic slab. In one of these cases, which I'm showing here, we considered the two umbral cores to be low beta regions and the slab, the light bridge itself, to be relatively weakly magnetized in a high beta region. For analytical solutions or approximations, we chose a weaker asymmetry so that the dispersion relation could be decoupled, made more similar to the symmetric case and handled easier. But for numerical solutions, we could still solve the full dispersion relation. So as you can see, a stronger asymmetry was also allowed. So in this diagram on the right, you can see the phase speeds of waves normalized by the internal outplane speed plotted against the dimensionless slab width parameter. And the whole variety of waves here. So in this bottom region, in blue, we've got a quasi-sausage surface mode, and its pairs a quasi-sausage, quasi-king surface mode in red, which are followed by a whole wide region of body modes above. Again, quasi-king modes are plotted in red and quasi-sausage modes in blue. And these ones especially can span a wide range of phase speeds as we change how wide our slab is. So I've only shown you one case, but even in this one, it seems to be that there could be several types of waves we could detect and then use for seismological purposes. And then there's the whole question of how realistic were these values. We could choose entirely different ones and find a whole lot more of wave solutions. Then the other application I'd like to mention is magnetic breakpoints. So these are areas of concentrated magnetic fields sitting in the intergranular lanes, embedded between two separate granules. So again, they are ideal candidates to be looked at as an asymmetric model. And well, there have been various estimates for the sizes. Usually they are like a few 100 kilometers across, and the shapes are highly varied from irregular to circular. But it's been found that only about 2/3 of the cases do isolated MBPs have circular shapes. In many other cases, they are actually quite elongated, so we can, as a first approximation, apply a slab model to them. And this is an especially exciting application because they are quite small, as I've said, so we haven't been able to look at much yet, but now with the newest generation of solar telescopes like VKIST, we might have enough pixels across them to apply our magnetic seismologic techniques. So again, we've looked at these breakpoints in analytical approximations, and we found numerical solutions as well. Interestingly, so first we took the whole system to be high beta regions all across, and we found that there is a quasi-sausage surface mode and a quasi-king surface mode that's supported by the waveguide. And this didn't really change strongly when we changed the internal region of the slab of the brine point to be of intermediate beta value or even low beta. So we still found the same type of solutions, even though their frequency were a bit different. But as the ever-growing family of asymmetric slabs show, there is always more room for improvement. So we can incorporate more and more factors in our models that influence solar atmospheric features, such as the bulk background flows I mentioned. And why perfecting our descriptions like this is so important will be very clear when we add some asymmetric downflows in the intergranular lanes to this model. So as you see, the solutions suddenly change drastically. And I'm almost at the end. I just like to say that thanks to adding these flows, for one thing, the Kelvin-Helmholtz instability could appear for a small slab width. For the other thing, we've still got surface modes like before, but we've also got an additional band of body modes that became possible. In conclusion, then I'd say building up our model step by step like this allows us to get an insight into how different types of asymmetry influence solar atmospheric features. And in turn, that further motivates us to keep expanding our models with new physics. And maybe it will allow us to approximate this, certain phenomena in the solar atmosphere with greater precision. Thank you for your attention. And if anyone's interested, there's a whole long list of publications in the SLAB family, whichever one you'd like.
Thank you very much, Naomi. Very interesting talk. We have one question already in the Q&A from Julia Reel, who says, the eigenfunctions of surface and body waves you showed look very similar. Can you really distinguish them as surface body waves in this case?
Yeah, go back. I mean, it's easier to distinguish them if we've got more oscillations of the body waves inside. So this, we've just got the one maximum in here. But as we go up to the higher harmonics, there would be more maximum and minimum and null points in there. So that would be, you know, if we choose a solar feature that we can actually observe in detail, so not yet an MVP, and looked at it, if we saw a whole bunch of maxima in there, then it would be very easy to see that's body wave.
Okay. So thank you. If there are no further questions, I'd like to thank Naomi again. And now we're going back to Angela Bautista, who is going to give the talk of direct observational indications of wave-like disturbances in MVP tracks. So if you'd like to try and share your screen.
Yeah, good afternoon. I'm sorry for the inconvenience.
Seems to be there.
Okay. Good afternoon, everybody. My name is Angela Bautista. I'm an undergraduate physics student from Universidad Nacional de Colombia, and I'm going to present a project that we developed in collaboration with the University of RAS with the program Vision Research. Okay, I would like to start giving a brief description of the contents of the talk. First, I'm going to give you the theory behind MVPs, then a description of the observational data, and finally, well, the results and our final work. Okay, so for this introduction, I would like to say that our region of study was the quiet sun. This is the region outside of really active suns, which are sunspots, sports, and plages. And this, the quiet sun is dominated by granular convection. And this bright region that you can see here in between the granules are magnetic bright points. These are small scale magnetic features which have strengths in the order of the kilogauss. They have lifetimes of 1 to 2 minutes and diameters of approximately 200 kilometers. A theoretical model that explains how MVPs are formed is the convective collapse model, where these MVPs can be thought as foot points of the thin magnetic flux tubes that thread the corona. And they can generate magnetohydrodynamical waves that can contribute to the coronal heating. And these magnetic flux tubes can present different modes of oscillation. We have, for example, pulsage, kink, acoustic, and torsional modes. Okay, the data that we used for our analysis was taken for the Solar Optical Telescope, which is an instrument which makes part of the Hinode mission, on board the Hinode mission. It has a primary mirror with a diameter of 50 centimeters, which allow us to have images with a spatial resolution of 0.2 arc seconds. Our aim was to study MVPs in 2 consecutive layers of the solar atmosphere, the photosphere and the lower chromosphere. We considered images in 2 filters, in G-band and in calcium. We had a data set of approximately 180 images with a spatial sampling of 0.054 arc seconds per pixel.
These are the images that we obtain with the SOT. Here in the left, you can see the image in given filter, and here is the image with the calcium filter. We focused our attention in one isolated MVP, which is located inside the area enclosed by this square. The first step to do this analysis was to identify all the magnetic bright points in our images. To do this task, we employed an algorithm developed by Dr. Dominic Woods for the detection of the MVPs. This algorithm takes into account three characteristics of MVPs: the brightness gradient, and the size of the feature, since they are small scale features. So these algorithms employ first segmentation algorithm to determine the size of the features. And then with the other two characteristics, it identifies the magnetic bright point. So we can see here like a summary of what the algorithm does. Here we have the image in event. Then we have our image completely segmented. Here is the same image, but we are showing here all the borders of the segments. And finally, we have our image with our MVPs identified, as you can see here in yellow. And so in order to do an analysis of the two layers of the atmosphere, we created a code to determine common points in these two filters. Oh, no, I'm sorry. We applied this identification algorithm to our images in given. But in calcium, as the granules appear dark, we had to do an inversion of the images, and then we applied the identification algorithm. Here with this green cross, we are showing you the MVP that we are studying here. And then we apply this algorithm for our common point identification. And this code, for example, here we have a point in the photosphere. And then it looks for a point that lies in this region inside the circle of radius epsilon. So for example, here in the photosphere, we have this, and in the lower chromosphere, this pink point, its barycenter, it's inside this circle. So we can assume that it corresponds to the same point. And then once we have our collection of all the common points in the two layers, we applied a tracking algorithm that applies almost the same principle. But this time we have here images in the same filter. So we have, for example, here 0, T1, and G1. And it looks for the same. For example, here in the next time step, it looks for a point inside the circle of radius epsilon prime. And in this way, we can obtain like a path of our MVP. We can track its movement. This is the results that we obtained for our MVP. Here in green, you can see the path that it followed in event or in the photosphere, and in orange in the lower chromosphere. In each number represents one step time. We can also see that the displacement is really small. We have here 54 arc seconds to 54.6 arc seconds. So it's almost not noticeable. We also did an analysis for the displacement vector, which is defined as this vector that goes from the first time step in the photosphere to the first time step in the lower chromosphere. And we define this vector for each time step. Then we calculate the mean displacement vector, which is represented here with this red vector. And then we calculate the difference, r minus d vector. We have this r prime vector, which is the one that is represented here for each time step. And also we obtain the longitudinal and the transversal components of this R prime vector in order to see oscillations in the amplitude and on the orientation of that displacement vector, which is represented by this angle gamma. We interpret these oscillations for K1 and K2 as kink modes. And here are the results that we obtained for its amplitudes. So we have here in red the longitudinal component and in blue the transversal component. Since the inclination of the flux tube can be affected due to the acceleration, we try to do a correction with this square trend. So we normalized our results with this square trend, and we obtain this corrected data. And then we fitted a sinusoidal function to the longitudinal and the transversal kink modes. And in order to do a similar analysis, but this time we try to detect such modes, we did a similar analysis for the evolution for the size and the intensity of the MVP. For the size, we consider that they have circular shapes. So we did an analysis with the diameter. Here in purple, you can see the evolution for the diameter in calcium and green in image event. And we did the same correction with the square trend. And here is the same analysis for the intensity. So we perform this modeling in order to look for a fast or a slow sausage modes. Since if they are in phase, the diameter and intensity oscillations, we can talk about a fast mode, and if they are in antiphase, we can talk about a slow mode. So our take-home message or the summary of this talk is that we implemented processing methods, image processing methods, to align to pixel level the images from both filters, and well then identify the features and properties of the features, such as the intensity, the diameter, and well the oscillations in the signal. We create a tracking algorithm to see how MVPs behave in time. And we found like an evidence of MHD characteristic modes in this small scale flux tubes. And some of the future work that we would do, this is an observational study. So maybe all the people that work with modeling can perform simulations in order to reproduce our results. Also, we can look for a large data set of MVPs in order to study statistics, and maybe to acquire observations with better resolution instruments, for example, the KIST telescope. And well, we are working on an article. If you want more information, you can look for it. Thank you so much.
Thank you very much. Very, very interesting talk. Do we have any questions? One from Mihaly.
Yes, thank you. Thank you very much for your talk. I guess the question I want to ask is, what fraction of the bright points that you identify in the photosphere are actually also identified in the chromosphere? So what fraction of those that we see in the G band can actually be picked up in the calcium too?
Okay, well, there are actually really few. I remember that we had identified, for example, I don't know, 180 MVPs, but then when we tried to find the common points were like 40 or 30. And then when we tried to follow their path, there were like one or two, because their lifetimes are really short.
Okay, thank you.
Okay.
Is there a question from Alex Shukabatsky as well? I can allow you to talk. There you go.
Well, what did you mean by the longitudinal kink mode? Is it like a propagating kink mode wave, or what did you mean by longitudinal? You said something about longitudinal kink.
Yeah, well, I mean the longitudinal component of these are prime vector, but
Okay.
the oscillations in this K1 is the longitudinal component, right? And K2 is the transversal, and we interpret its oscillations as kink modes. But
Okay,
as I
thanks.
said, it's an observational analysis. Yeah.
Okay.
Our
Thank you.
interpretation.
Okay, I just have a quick question if no one else does. So you track the motions in the photosphere and the chromosphere, and it seems like there's no time lag between the motion where the movement in both of these layers. Is that correct?
Well, actually, here you can see that there's a slight shift, but we try to align our images with a cross correlation technique. But
this is a shift spatially. I was meaning
yeah.
temporally, so we might expect. So I was just wondering whether the whole tube is moving as one, or whether it's being moved from the photosphere, and then that motion you'd then pick up 20 seconds later, say in the chromosphere, or whether there was a temporal lag.
Yeah, I would say that it's a temporal lag because the photos were not taken in both filters at exactly the same time.
Okay.
Yeah, but we try to align the images as well.
Okay, well, thank you. If there's no further questions, thank you again. It's a very nice talk.
For the opportunity.
Okay, so we've overrun a little bit, so we'll move on straight on to Ben Snow, who's joining us from Exeter. Would you mind? Oh, there we go. So if you'd like to share your screen, Ben, if you can. Yep, there we go.
Right, can you hear me?
Yes, I can hear you.
Okay, great. So my name's Ben Snow. I'm a postdoc at the University of Exeter, and I'm going to talk about mode conversion of two fluid shocks in an isothermal stratified atmosphere. So waves can naturally steepen into shocks as they propagate upwards in the solar atmosphere. So if we take the Val-C temperature and density profile and we specify a small linear wave, as it propagates upwards, it can naturally form a shock. So this is thought to be the mechanism behind things like umbral flashes. But with shocks, they can also undergo mode conversion. So this was studied by Pennicott and Kelly. So they had an isothermal temperature and a stratified atmosphere, so their density decreases with height. Specified a linear wave, it steepens into a shock, but as it passes through this line here, and this is the line where the sound and the alpha speed are the same, it separates into its fast component, which is this orange line here, and a slow component here. You can see it's separating into a very sharp fast component and a smooth slow mode wave. So as the shock passes through the mode conversion, it separates into its components, but this mode conversion height can occur in the lower solar atmosphere, which is partially ionized. So it includes both ionized and neutral species. So we need to take into account the neutral species to really capture the behavior of the shocks well. And one of the key consequences of partial ionization for shocks is that you end up with a finite width to your shocks. This is something which Andrew and I have studied quite a lot over the last few years. So what I'm going to be talking about today is how this partial ionization affects the mode conversion. I'm going to be doing this via a load of numerical simulations using our two-fluid code. So we're using the two-fluid code called the PIP code. And this evolves for a neutral species, which is essentially a hydrodynamic species, a charged neutral ion plus electron species, which is essentially an MHD type fluid, and they're coupled together using thermal collisions. Okay, so the atmosphere I'm going to be using is relatively simple. So we're going to have an isothermal atmosphere, and I'm going to be comparing everything to an MHD model. So for our MHD model, what we'll do is we'll calculate the pressure using the integral of the pressure scale height, use the ideal gas law to then get the density, and then we can see the density follows this black line here. And for this MHD model, our mode conversion occurs at this black vertical line. Now, for our two-fluid model, we have both the plasma and the neutral species that we need to work out the profiles for. So we'll do the same procedure, and we'll normalize everything such that for the plasma component of the two-fluid simulation, we have the same density as in our MHD case. So there's a nice blue dashed line fitted over this black line that you might just be able to see. And what this means is that if the fluids were completely decoupled and the plasma was just doing its own thing, it would behave exactly like the MHD case, and the mode conversion would occur at this black vertical line. Okay, now on top of this plasma density, we also have a neutral density. So our neutral density is given by this red dashed line, and you can see it's steeper. So it's steeper because it's got a different pressure scale height. And we set a neutral fraction to be quite high at the base, so it's set to be 0.999 at the base. So it means that it's almost entirely neutral at the base of our domain, but because of the different pressure scale heights, it becomes less neutral as you propagate upwards. And what we have is, well, for the two-fluid model, we can consider two different mode conversion heights. The first is this black line. As I said previously, if the fluids are completely decoupled, the plasma should just behave like the MHD model from how we've normalized things, which mode conversion would occur here. Now, if we think about the fully coupled system, we have to include the neutral pressure and the neutral density in our calculations of our sound and alpha speed. So that means our mode conversion height moves. So our mode conversion height is then this green line. So if it's fully coupled, we'd expect it to mode convert up here. If it's fully decoupled, we expect mode conversion to occur down here. And if it's finitely coupled, we'd expect somewhere between the two. So that's one of the things I'm going to be talking about. Okay, and I guess one last thing to point out on this slide is that our two-fluid model has more mass, more total mass than the MHD model because of how we've normalized things. Okay, so let's look at some simulations. So the simulation on the left-hand side, this is an MHD simulation. So this is a single fluid MHD with a stratified atmosphere. So we specify a linear wave at the base of our domain, propagates into a shock below the mode conversion height, and as it passes through, it separates into a fast component, which is this sharp, fast shock here, and a smooth slow mode wave, which is this solid black line here. One thing I forgot to mention was that we have an inclined magnetic field. So the inclined magnetic field allows the fast mode and the slow mode to exist at the same time, or allows it to separate into a fast and slow mode. Okay, so with the MHD model, we're seeing that we get a nice sharp, fast shock and a smooth slow mode wave. And this was more or less what was shown in the Pennicott and Cali paper as well. Now if we do the same simulation in our two-fluid model, so this time we have neutrals in it as well. So we specify a small linear wave, it steepens into a shock below the mode conversion height, and then as it passes through this, it separates into a fast component, which are these dashed lines, and slow component, which are the solid lines. Now, I know there's a lot of lines on here and it can get quite confusing. In this talk, black will always refer to a plasma species, red will always refer to a neutral species, and the main component which I'm going to be talking about here is this black dashed line, which is the fast component of the plasma. So if we look at the fast component of the plasma, this black dashed line, we can see that it looks pretty different to the MHD one. So in the MHD one, we've got this nice sharp shock. In the two-fluid sense, we have this fairly rounded shock. So it still satisfies a fast mode shock transition, but because of the influence of the neutral species, we now have a finite width to our shock, and it's quite a large finite width. So this finite width, we'd expect it to be related to the level of coupling of our system. So if so we can investigate what happens if we change the level of coupling of our system. So let's show the MHD one again. So this one is, we understand this very well. Linear wave steepens into a shock, separates into a fast shock here, and a smooth slow mode wave. And you see this fast shock is nice and sharp. And if we think about a two-fluid model that is very, very weakly coupled, so here I've set the collisional coefficient to 0.001. So this means that we expect collisions to occur on timescales of 1,000, but the timescale of this simulation is about 5.5, so we're not expecting many collisions to have occurred. And this is mirrored in the results. You can see that it's more or less doing it, the plasma and the neutrals are more or less doing their own thing, and plasma is behaving just like the MHD case with a nice sharp shock in the fast component. Okay, if we increase the coupling up to 3, so here we're expecting there to have been tens of collisions, so we're expecting it to be weakly coupled, we can start to see that this fast mode shock is experiencing some collisions with the neutrals, as evidenced by the slight roundedness of the shock, and there's now a finite width to our fast mode shock. And there's a new plot on the far right here. So this plot shows But this black dashed line is the location of the fast mode shock, and the solid line is the location of the slow component. And this shows where the fast shock separates from the slow component relative to the mode conversion height based on the plasma properties only, which is this green line, or the bulk properties of the system, which is this blue line. So here the coupling is fairly weak, so we're expecting the mode conversion to occur closer to this green line, and that's what we're seeing. We're seeing this black dashed line is separating from this solid line closer to this green line, so it's behaving. So while there is some influence of the neutral species, the mode conversion is occurring at the same height as which it would for a fully ionized system. Okay, if we increase the coupling even more up to 10, so this is, we can see more influence of the neutrals on the fast mode shock. So the fast mode shock in the plasma is getting a bit more rounded, and we can see that this this black dashed line is starting to collapse onto this solid line, so the mode conversion is starting to occur a bit higher. If we increase the coupling even more, so this was the simulation I showed before, so we're expecting there to be hundreds of collisions at this time, and you can see a very, very broad shock in the plasma. And if you look at where mode conversion is occurring, it's occurring somewhere around here. So it's between the two limits. So the place at which mode conversion is occurring depends on the level of coupling of our system. And if we increase the coupling even more, what we see is that this is getting towards thousands of collisions. We're seeing that the drift velocity between the fast mode shock and the corresponding movement of the neutral species is decreasing. So the system's coupling together more, so it's behaving more like a bulk fluid. And as this is shown in here, with the separation occurring above the blue line, which is the mode conversion height based on the bulk properties. And if we keep increasing our collisional coefficient up to 300 and then to 1,000, we can see that here our drift velocities are very, very small. So it's behaving like a bulk system. Okay, but one other thing I'd like to point out with this is if we look at the width of the fast mode shock, so here it's discontinuous. If we have a finite width, it gets a little bit broad, it increases in width, and then as we go towards infinity, it decreases in width. So we're seeing the width of the finite shock is proportional to the level of coupling of our system. So we can plot this. So this, on the vertical axis, is the width of the fast mode shock, and this is in units of pressure scale height. And along this axis is the level of coupling of our system. So if we have very, very weak coupling, the neutrals and the plasmas aren't interacting too much, so we're getting more or less the MHD shock width, we're getting this discontinuous jump. As we go towards a finitely coupled regime, we start to get this fairly broad fast mode shock. And then as we tend towards infinity, the neutrals tend toward, the neutral and plasmas tend towards a bulk system, which is fully coupled. So the width of the finite width of the shock decreases. And if we went even further, we'd expect it to become discontinuous again. Okay, but from this, we can see that we're getting a very, very broad finite width. It's around about and even exceeding a pressure scale height of the system. So our fast mode shock is becoming excessively broad. And if we think about what this might look like from an observer's point of view, so if we just plot the line of sight velocity and we sample at a certain height, we can plot this as a time series of our Doppler velocity. And these red lines denote the start and finish of the fast mode shock. So we're seeing that we're getting a fast mode shock would appear as a gradual rise in Doppler velocity over a certain time period. And if we put in characteristics, properties of the chromosphere, this comes out as being about 6 seconds. So we're seeing that a two-fluid fast mode shock could exist as a gradual rise in Doppler velocity over a few seconds. So this might be a potential observable of two-fluid effects in the solar atmosphere. So that's all I'm going to talk about today. So I've presented a few of the results from the mode conversion, from the two-fluid mode conversion work that Andrew and I have done. And what we've seen is that the height at which the mode conversion occurs depends on the level of coupling of your system. I've also seen that the finite width of your fast mode shock can become much larger than the pressure scale height due to the influence of the neutral species. And this leads to a potential observable of two fluid effects as a gradual rise in Doppler velocity over a few seconds. So if you are interested, I'd encourage you to check out the full paper, which is Snow and Hillier 2020 in ANA, and thank you for your attention.
Oh, thank you very much, Ben. It's a very interesting talk. Are there any questions in the chat, the Q&A? Hands up. I'll start it off. So you're talking about the gradual rise in the Doppler velocity. Do you have could you quantify that? Are we talking about 1 or 2 kilometers per second, or 10 kilometers per second, or?
I was thinking more just in terms of the I guess this is normalized by the sound speed, so it would be a gradual rise. So it's 0 to 1.5-ish, times by 8 kilometers per second. So it'd be around about 12 or so, a jump of 12 or so kilometers per second, but it probably depends quite a lot on the strength of the shock that you have.
Okay. That's observable numbers. So we've got Alex Shukabatsky has a question again.
Would the model be more accurate if you add, let's say, kind of like n numbers of fluid? So if we have more fluids, would it be more accurate, or so is enough to be studied?
It may be more accurate, but I doubt it. So if you're adding more fluids, I mean, the obvious choices would be to add more excitation states of hydrogen and allowing them to move separately. But then you have to incorporate things like your ionization rates and your recombination rates, and you have to advance the physics quite a lot more. So including more fluids, I doubt it would be anywhere near as important as including more realistic physics in the system.
Okay, great, thanks.
Okay, so if there are no more immediate questions, I'd like to thank Ben again. Very interesting talk. And now we go back across to Leuven to Julia Riedel, who's going to give us a talk about finding the mechanism of wave energy flux damping in solar pores using numerical simulations. So please take it away.
Yes, hello, good afternoon. Can you hear me all right?
Yes, we can hear you.
And you see my screen?
Yep, it's now in full screen.
Perfect. So now that the technicalities are done, I'm talking about finding the mechanism of wave energy flux damping in solar pores using numerical simulations. So the contents of this presentation were recently published in ANA. Solar pores are these structures of highly concentrated vertical magnetic field in the photosphere. So very similar basically to sunspot umbra. And they are good waveguides, and due to their cylindrical geometry, we often find tube waves like sausage and kink waves in them. So a lot of people have already talked about those today. And there are many observations of waves in solar pores. And one of them was done by Gilchrist Miller et al. 2021, where they observed 5 solar pores assembled in a neat row. And pore 3 here in the middle was the nicest pore in their sample. And they measured and found that the energy flux in pore 3 with height is strongly declines with height. So there's a very strong damping of the wave energy. And similar values were already found before by Grant et al. 2015. Now there's the question, why does this strong damping occur? What's the damping mechanisms? Well, there are a lot of different candidates. It could be reflection or refraction, resonant damping, damping due to electrical resistivity, damping due to leaky waves or mode conversion, or some frequency dependent damping like radiative or conductive losses. So some of those papers listed here have tried to directly explain the damping from Grant et al. 2015. However, they couldn't fully explain this strong damping. So the aim of this project is to do simulations of a solar pore and see if in our simulations we achieve the same amount of damping as in pore 3 of Gilchrist Miller 2021. And if yes, which damping mechanisms occur in our simulations. So here you see basically the model we are using. The pore itself is located here at the left side of the plot, with the pore axis being located at the left boundary. And the vertical magnetic field, or the magnetic field strength in our model, which you see here in the green lines, is very similar to the observational parameters that Gilchrist-Miller found, which are plotted here with the black lines. However, when we look at the density, in our model, the density is much less stratified with height. The reason is that we needed to somehow build a magnetohydrostatic equilibrium, and we tried to have a pore model as closely to pore 3 of Gilchrist-Miller 2021, and so a stronger stratification for rho was not possible to have a magnetohydrostatic equilibrium. Note that the plasma beta for our model is greater than 1 everywhere. Now to the boundary conditions. So at the loop X axis, we put reflective boundary conditions. At the top and outside, we put open boundary conditions. And at the bottom of the domain, we just put a simple harmonic driver with vertical velocity. Now, if we apply this vertical velocity driver at the whole bottom boundary, this is what simulation looks like. So you see here the vertical velocity perturbations. And if we now calculate the energy flux with height, do we get the same damping as in the observations of Gilchrist-Miller et al? Well, no, not at all. The observational values you can see here with the black dots and the black line, and the values we get from the simulation, you see it here with the solid green line and purple dashed line. So we don't see a damping at all in our simulations, and that's not only true for ideal MHD, but also when resistivity, viscosity, or thermal conduction are included. And the reason why in our simulations the energy flux even increases with height is that energy flux from outside the pore is refracted into the pore. So now let's just change the driver location. Instead of driving the whole bottom boundary, we just drive the system locally inside the pore at the location that's marked here with this red bar here. And a driver like this can be justified because since solar pores are good waveguides, it's okay to assume that waves are mainly present inside the pore and not outside. Okay, now we calculate the damping for this setup, and voila, just by changing the driver location to a local driver, we get very strong damping, as you can see here. And this damping in our simulation occurs because of two geometric effects, A, geometric spreading, and B, lateral wave leakage. Let's first talk about geometric spreading. So as you can see here with the gray lines, the magnetic field and also the pore radius diverge with height. So if the waves propagate really strictly along the magnetic field line, we would of course expect damping due to geometric spreading, because at greater heights, the flux would be fanned out over a wider area. And this damping would be proportional to 1/r, because we're here in a 2D geometry. And this 1/r line is plotted here with the red dotted line. The green solid line is the damping occurring in our simulations. And this green line here is the same as this on the left side for comparison. And you see that the red dotted line for geometric spreading is quite far away from the green solid line. So clearly, if we would only consider geometric spreading, there is clearly a damping mechanism missing. Also, if you would integrate the wave energy flux for every height across the pore, and only geometric spreading is at work, then you would consider that value to be constant with height. But it isn't, which you can see with this orange dash dotted line. And finally, you can see there are clearly waves outside the pore. So some energy must be lost because waves exited from the pore. And this damping we call damping due to lateral wave leakage. So here I will show you some movies of the wave energy flux. The left one is wave energy flux parallel to the magnetic field. And you can see clearly there's wave energy flux leaving the pore. And here, these shapes here propagate with the same speed and the same shape as the theoretically predicted fast wave fronts. And now we look at the normal component of the energy flux. There you see the same. There are also some slow wave features you see in between those dashed lines, the dashed green lines showing the theoretical slow wave fronts. So to conclude, we have both fast and slow waves exiting the pore, and fast wave energy flux is lost from the pore. Now let's get an estimate of if this lateral wave leakage really contributes to the damping. And to estimate that, we calculate the energy flux present on this field line here, which is routed just outside the driver location. So this over the total incoming flux. And the damping associated with lateral wave leakage is then 1 minus this ratio, and is shown here with the blue dashed line. Now this blue dashed line is very close to the green solid line, meaning that it's probably a bit of an overestimation for the effect of lateral wave leakage. Also, the orange dash dotted line is somehow an estimation of the effect of lateral wave leakage. So the real contribution probably lies in between the orange and the blue line. So we can say it approximately has the same effect of for the damping as the geometric spreading. Now I told you in the beginning that in our model, plasma beta is greater than 1 everywhere. Also, this is just a 2D configuration, so basically a slab model. However, we recently did some new simulations for our new project, where we simulated a 3D corner loop, and around the foot point of this 3D setup, which you see here, we also encountered lateral wave leakage. So those are these shapes here. So there's clearly, again, in our new simulations, waves leaking laterally outside of the loop. And this happens in the high plasma beta regime, and also here in the low plasma beta regime, with plasma beta equals 1 is the green line here. So to summarize, we did simulations of a solar pore that was driven at the bottom boundary. If we drove the system at the whole bottom boundary, then we didn't encounter any damping. However, if we used a localized driver just inside the pore, a strong damping was achieved by geometric spreading and lateral wave leakage. So we can say that just by considering some classic wave effects, you can already achieve very strong damping. Thank you very much. I'm happy, of course, to answer any questions now. If you would like to take your time and go through the details, I would like to refer you to the very recent paper. Since my name seems to be quite unique in the solar physics community, I'm sure you will have no problem finding it on ADS. Thank you.
Okay, thank you very much for the very interesting talk. Robertus is straight up, his hand is straight up.
Yeah, I wanted to write off the question, but I couldn't, but thanks, Chris. Julia, this is a nice talk, but can I just clarify with you something? It looks to me that you kind of mix up a little bit damping and attenuation, right? So I think I don't know who is your supervisor or who you do the PhD with, but I think you should have a word with him or her and look a little bit into this. Attenuation is not the same as damping. So when you were referring, for instance, to the observations of these 5 pores, I am not sure if it was damping. I think it was attenuation. If you want to have a look of a similar example where damping was found, then maybe you could look at a paper where Chris was a co-author and Nabil Frege was the first author, where we actually looked into some damping. You know, damping will result in true energy loss. Yes, attenuation is something different, and I think you have to be careful with this. That's all.
So it's mainly about the nomenclature, like how to call it.
These are different physical phenomena. If you have attenuation, the fact that energy spreads out, it doesn't mean it's lost from the system, right? The total energy in the system is the same. However, if you have dissipation, you know, true physical dissipation, then you have heating, for instance, you know, you will actually increase entropy in the system, right? With attenuation, you will not increase entropy in the system. So these are different physical mechanisms. Sometimes, and I'm not blaming you for that. Sometimes, for instance, leakage is considered as damping, but I think it's not correct physically. Unfortunately, you know, we all make mistakes in our papers, and sometimes we don't spot it on time, and then it spreads, etc., etc. Okay, but damping.
Okay, thank you. I will take this into account. Maybe I should call it then flux decrease with height or something like this, because
I
this
think
would
look into this carefully, because you could have damping. In your code you do have dissipative effects. That's why I think it's a more subtle question. Just look into it with, I don't know who is your supervisor, Tom.
Yeah, Tom van Doorselaar.
Oh, he knows this very well. Yeah, he knows this very well. He's an expert in this.
Thank you for your comment.
You're welcome.
Thank you very much. So we have one more question from Tim Duckenfield, who says, excellent talk. Thank you, Julia. Can I ask, is there any evidence in that observation of 5 pores in a line of the driver being localized to individual pores, as your simulation results would imply?
Let me think. It's been a while since I looked at that data. I think there was like in the paper of Gilchrist Miller, you did see clearly like energy flux in the pore, so which was damped much less than the energy flux outside the pore that they measured, saying that those are, you know, good waveguides. So it would make sense, but I'm not that familiar with the observational values itself.
Okay, thank you very much. So if there are any further questions, Tom has replied in the chat and said, so it should be resonant attenuation, but we'll leave the discussion of this for another time, I guess. So thank you again, Julia. It's a very interesting talk. And our final talk of the day comes from Thomas Howson up in St. Andrews, our final, last but not least, shall we say.
Definitely last.
Yeah.
Won't comment on the other. Can you hear me? Yeah.
Yeah, we can hear you. And
play, and you can see that.
Yep, that's now full screen. So please take it away.
Great, thank you. Thanks everyone, and thanks to the organisers for hosting this really interesting session. Today I'm going to talk about basically, quite a small project I've been doing over the past few months, which looks at the Kelvin-Helmholtz instability driven by oscillatory shear in coronal plasmas, and whether or not that can drive, or whether it will drive, magnetic reconnection. This was partly motivated by people's discussions in Prof. Nakaryakov's birthday conference before Christmas now, where a general feeling is there's not necessarily much energy in the waves that drive the Kelvin-Helmholtz instability. So there's not necessarily enough energy to do much heating there. But whether or not the instability can drive reconnection of, say, the background field, and that's using a relatively simple model, what I wanted to tackle here. So I'd also like to say thanks to David Pontin, who's been able to help us from the magnetic reconnection point of view, because it's not something we knew too much about going into this. Sorry, I need to move my something on my screen. Okay, so the idea is there's been many works on this, some references down at the bottom. Sorry if I've forgotten you, but I was focused on doing these cartoons rather than references. There we go. So you may have some coronal loop which oscillates forwards and backwards, and very rapidly you will see that the amplitude of this oscillation decays, and usually that's attributed to resonant absorption. There will be some density profile across the coronal loop, and there will be a resonance that exists in the boundary of the loop, and the transverse kink motion will transfer energy to these azimuthal waves that are contained in the boundary. And that's the general theory behind it. As this happens, you'll also have phase mixing that goes on in the boundary of the loop, and you'll have a velocity shear that forms, and under many situations that velocity shear will be unstable to the Kelvin-Helmholtz instability, and the instability will deform the boundary layer or the whole loop, depending how hard it's driven, and a few different things. And that's interesting from a wave heating perspective because it generates lots of small length scales, which means energy can be dissipated more efficiently. That's not working. There we go. So this is just a general flowchart of what wave heating looks like. Because of the high Reynolds number in the corona, we need to generate small length scales. So you need coronal waves that we observe might have large length scales, and there have been many different mechanisms posed for a mechanism for which the long length scales in the observed waves can be, the energy can be transported to short length scales and dissipated. So in the model I'll look at today, the KHI has two important effects that are interesting in the context of wave heating. The first and most obvious one is that it creates small length scales, which will enhance the heating rate. And then the second one, which depending on the setup of the model, as the loop deforms, it will change the natural frequency of the field lines there. And we'll see evidence of that in the model I present. And that in turn, if you're driving with a simple harmonic oscillator, which may or may not be physically relevant, that will change how much energy gets input into the system. And then coming back to this, is there enough energy in the waves? Maybe, maybe not. And the question we're asking is, well, how can the KHI extract energy from the background field, if indeed it does? Okay, so our model, I had this cartoon of this azimuthal wave before. Essentially, we're just going to take a cut of this and put it into some Cartesian geometry. So we'll have field lines in the Z direction, we'll oscillate in the Y direction, and we'll have some density profile in the X direction, which means there's a change in the Alfvén speed along these field lines. And we're going to drive from the bottom boundary, and we're going to drive in such a, well, with an amplitude of 7 kilometers per second. We're going to drive, it's going to be like 7 times sine omega t everywhere on the bottom. That will send waves up these field lines. It'll hit the top, bounce back, and you'll get a reflected wave. And we drive with such a frequency that this central field line, we drive with the natural frequency of that field line. And you'll see that shortly. So as we drive from the bottom boundary, a wavefront propagates up, and we'll have classic phase mixing because of the gradient in the Alfvén speed. So naturally, you'll create small length scales here. The wave hits the top boundary, bounces, and it'll keep bouncing forward and backwards as we keep driving. Now, once the reflected wave returns to the bottom, in most places, the driver won't input any more energy. It's as likely to take energy out of the system as it is to put into the system. However, on the central field line, where we're driving in some sense with the correct frequency, you'll have a resonance that forms, and that means you can very efficiently inject energy onto this kind of plane of field lines. X is 0 that comes into and out of the screen. Now, after some time, because of a combination of these two effects, you'll have the resonance that forms at X is 0, and it'll have associated with it a large transverse velocity shear. Now, there's been lots of work done on this, I've said, that says this is very often unstable to the Kelvin-Helmholtz instability. Don't worry about the different lines here, they're just different cases in our parameter study. So probably most of you have seen this before, but this is how the KHI develops in our system. So on the left, we've got a density profile, which you can see initially some large vortices developed, and then after a while, you kind of get this turbulent-like mess. And on the right, again, you've got the density, which is the contours, but the arrows are also showing the velocity vectors. So you can see, say, if you walk along this line, that there's small scales in the velocity field. And because the magnetic field is frozen into the plasma, you'll also get small scales in the magnetic field. And you can do heating. So in this case, the KHI develops after approximately 4 driving periods, although we'll see in some cases it's a bit longer than that. And we really want to ask, once we reach this turbulent region, I grab this. Once we reach this kind of situation when the field lines are all being sheared next to each other, how much reconnection do we get in like an ordinary straight field case? And if there's also shear in the background field, do we get any more or less reconnection then? A quick word on the Poynting flux. So this surface plot here is if I kind of average along the bottom boundary in Y, so this is in the direction of my gradient in the alpha speed, how much energy do I put in? But you can see the formation of the resonance of being this peak, whereas everywhere else you don't really get very much energy. This black contour here is, according to Withrow and Noise's 1973 something, can't remember, paper, how much energy you'd need to heat the quiet sun. So for our 7 km/s driver, which maybe isn't that high, most of the domain, you don't get enough energy to heat the quiet sun. It's just close to the resonant layer. The KHI does disrupt the resonant layer. So right on the resonance is this black line. You can see when the KHI happens, because the resonance is disrupted or extended perhaps, actually on the x = 0 line, the energy injection rate decreases. The red line is slightly off the resonant plane, and you can see here, well, everywhere else you'll get a beating effect in the energy injection until the KHI happens, and then over some slightly broader region than initially, you can get enough energy in. But that's to say, the KHI doesn't really disrupt the field lines enough to broaden the resonance over much of the domain in this case. So I want a few different examples so we can look at the magnetic reconnection rate for when the growth rate of the KHI is lower. So I have 2 different cases. I have shorter field lines. Now, shorter field lines will have larger magnetic tension for the same size vortex that forms. So in general, shorter field lines will reduce the size of the Kelvin-Helmholtz vortex that forms, which we see here. And another thing, and probably more interesting in the context of what we're trying to do, is magnetic twist. Now, I've got twists in inverted commas because in this Cartesian geometry, a twist from our coronal loop actually corresponds to just a shear in the background field, where some of these field lines on the right of the central field line are pointed into the plane, and on the left of the central field line are pointed out of the plane. And that will be our background shear. And again, it's been fairly well studied. The Kelvin-Helmholtz instability growth rate is reduced when you have this shear in the background field. You can see here, these are the 3 cases: no shear long field lines, no shear short field lines, and shear. That the largest vortices appear on this left-hand plot, and you get much smaller vortices, much smaller growth rates in the other 2 plots. Okay, so what I've just said is basically summarized in this plot here. On the left-handmost plot is basically showing our growth rate. So for shorter field lines, we get, it takes longer for the Kelvin-Helmholtz instability to form, so lower growth rates. And for more shear, which would be twist in the coronal loop, again, you get shorter field lines. For the currents, which is most interesting for the reconnection, and for the vorticity, which can also produce heating through viscous effects, you get the largest currents and largest vorticities during the growth rate of the instability, and then they fall back down. Okay, so for when we look at reconnection, the growth of the currents during the instability is what will be important. So this is what we were speaking to David Ponton about, really. So in 3D, in general, for reconnection to occur, you need the integral of E parallel along a field line to be non-zero. And the maximum value of this integral in a given non-ideal region will give you the rate of reconnection within that region. Now, when you have multiple distinct current sheets, things are a bit more complicated because you effectively have all these different reconnection regions working almost independently of each other. So you need to be a bit more nuanced with your approach, and you should use maybe this formula here from Wiper and Hesse 2015. Basically, you have to sum up this thing over local maxima and subtract the saddle points in between that connect the different maxima, and that will give you a global rate. This is what the integral of E parallel looks like in our Kelvin-Helmholtz vortices. So you can see the density deforming in the background, and you can see we obtain large values of the integral basically around the boundary of the Kelvin-Helmholtz vortices. So going back to our last plot, you can see there are these kind of two distinct large regions. So you'd kind of do work out the integral here, work out the integral here, add them together, and then subtract. You'd have to go and figure out where the saddle point between them is and subtract the value of the integral there. How that works in practice, so this took quite a lot of coding to do. The contour here is from 10,000 field lines traced on my bottom boundary. I walk along those field lines and say, what's the value of the integral? And that's what the contour is. The black points are me identifying some local maxima. Now you can see, say over here, I've ignored them. And I found that it just becomes really too complicated if I take every single local maxima. So, I only take local maxima above some threshold, which I've chosen just to be half of the maximum value. And those are these black points. And then I have to go and figure out kind of saddle points in between them all, which according to the code I wrote are all these different white points. So according to this formula, I add up all the black points and subtract all the white points. And I've actually shown the absolute value of the integral here. Sometimes you'll have positive, sometimes you have negative, but really you just want the positive bits. Sorry, you don't care about the sign, is what I should say. So once I've done this, I can do that at all different times, and I'll get a reconnection rate as a function of time. So as the KHI forms, I get these large currents, I get a high reconnection rate, and that's what's happening here with the black line. The black line is the same on both plots. That's my, in some sense, unsuppressed case where I have the highest growth rate of instability. So longest field lines and no shear in the background field. The shorter field lines, we know we have a reduced rate, so we can expect the reconnection rate to be lower and peak later, which is what we see by comparing the blue and the black lines here. The sheared field, on the other hand, this is kind of the more interesting thing, and this was, will the KHI really trigger the background field to start reconnecting? Now, this plot is not telling you whether it will or it won't. It's just telling you that if it does, it's not doing any more reconnection than the straight field case is anyway. So we know the instability happens a lot less in the blue case than the black case. But the background field that the background shear, the free energy that you have in the blue case compared to the black case, you don't really access it in terms of reconnection at all. I mean, if you do, it's still less than the reconnection you get just from the field being compressed in the unsuppressed case. Okay, so that's ultimately the conclusion of the talk. We see that in all cases, the KHI will trigger some magnetic reconnection. You see a big spike in the reconnection rate when the instability happens. And it's greatest during the initial phase, the initial growth phase of the instability. In agreement with previous studies, we see that shear in the background field and shorter field lines both reduce the growth rate of the instability. And then we see that regardless of whether you have free energy in the non-potential background field, which you have currents in the background field, they may, you might expect they might encourage some more reconnection. What we actually find that is in a case where the growth rate is lower, you'll see less reconnection, or a lower rate of reconnection. And the only way you could think to get around this is actually having the KHI to trigger a new regime of resistivity, which, I mean, you might say that happens. And of course, in that case, if you have no reconnection happening in say the background and the KHI comes along and you reach some critical current, then yes, you will get a significant amount of reconnection compared to say what was going on before. But in general, I mean, it's hard to argue whether you should do that or not. I think that's all I have to say. So thanks for listening. I wasn't too long.
Thank you very much. Very, very interesting talk. Are there any questions? Robertus is raised.
Sorry. Sorry. just ill since last Friday. Sorry. Thomas, well, I'm sorry. When you mentioned this 7 km/s driver, yes, and then you said that this is not much. Where is this driver acting in your model?
Sorry, so I mean, in general, we just have a coronal model. It's happening at the base of these foot points. So I should say, if I go to
hang on. So base of the foot point is then the photosphere, right?
I mean, yeah, we don't have a chromosphere, say, but yeah.
So yeah, so that's where but that's the physical model. Okay, you ignore the fancy chromosphere and all this transition in the interface region, but basically you drive the system with photosphere, right? That's the fundamental concept of your model.
I mean, given that we're ignoring the photosphere and chromosphere and transition region, I'd say that I don't know what the photosphere is doing, but at the base of the corona, we have 7 kilometers per second.
But then I don't know how would you drive at the base of the, you know, if you only consider, I have no issue with it if you ignore the chromosphere and the, you know, the transition region. That's not a point. But I think 7 km/s would be a very odd and strong driver. That's not the standard number for photospheric driver. It's maybe 1 or 2 km/s, which is a lot of, you know, from an energetic point of view, it's a big difference in your model. If you say that somehow it is line timed to the transition region, but then I would ask you the question, what is driving your system there with that amplitude? Then I would have that question. Okay.
Yeah, I mean, I think you can probably argue I mean, you could say whatever you want the velocity driver to be. I mean, I essentially just picked a number that produced, I mean, we're going to have a resonance forming. So to some extent, whatever you drive with at the bottom doesn't matter too much. It'll just take either longer or shorter for the resonance to build up here. And then for the instability to happen.
Well, it does matter, because if it takes too long time, your system is evolving in time, then the mechanism is not working. I think it is important.
I'm sorry, I don't really understand, because I mean the system, okay, I mean, it's a toy model, like the coronas can do whatever it wants, but if we drive with 2 kilometers per second in this model, which you can say, okay, the model is rubbish, but you will produce largely the same results. You'll just take longer for the instability to happen. I mean, it may happen at a lower amplitude than it does now, because you'll have smaller scales this way, because you'll have had more time to do phase mixing.
I don't think you should say the model is rubbish. All I'm saying is that just be careful with the application before you deduce too much how important it is.
Okay.
I speak of experience. I have done it before, unfortunately.
Okay. Are there any further questions? Now I have one quick one. Do you think these reconnection sites could be maybe the cause of these little jets observed by Antolin et al.?
I doubt it. To be honest, I mean, possibly, but I would think that that's more slow stressing of the field, probably, that then you get. Okay. I mean, possibly. I mean, some people might disagree with me, but personally, I don't think so.
Okay. So thank you all very much. Thank you again, Thomas. It's very, very interesting talk. I'm conscious of the time. I think we are going to be kicked off because there's the AGM for RAS very soon. So I'd just like to thank everyone for coming. I'd like to thank all the speakers for sticking to time and making it very easy to chair these sessions, and for giving the interesting talks. I'd like to thank all the attendees for coming.